Okay, good morning everyone. So I'm Luis Correa with the IST, the University of Lisbon, and Matti was kind enough to invite me to chair this keynote session. So we have 3 keynotes this morning, as you know, in the program. Basically, I just remind you who they are. So the first one is Kari Leppänen. I'm not sure if I pronounced your name correctly. Thank you. So it's coming from Huawei, and of course he'll be talking about all the wonderful stuff in 5G. And then we have Mikael from Ericsson, which is also addressing a perspective on 5G. And then we have Oppermann from New South Wales Data Analytics Center. For those of you that are wondering where New South Wales is not in Britain, is in Australia, right, Ian? And so he's bringing a vision on data, which is something we have been discussing a lot, not directly, but indirectly when we talk about verticals and all this kind of thing. So this is a very promising set of keynotes we have for this morning. And I will give the floor immediately to Kari. Let me just open the file here. So you're in charge.
Yeah, thank you. Thank you. Can you hear me? Hope it works. Okay, good morning, ladies and gentlemen. Yeah, I'm Kari Leppänen. I work in Huawei Helsinki office. I'm leading their team of 5G kind of network research people, and half of the team is actually in Stockholm. We have been working on 5G radio networks now for something like 4 years in this team. But okay, let's get going. Okay, so in this talk, I'll briefly talk about the path towards 5G. Then I want to give you an idea what mobile broadband may mean and what kind of huge demands for data there may be in future. Then a bit about many reasons to do network densification and also a bit about how to do it. Then I'll talk about the future kind of new role of future access networks. Then a bit about micro operators, and then give some opinions what 5G is good for and what it should not be used for, and then some recommendations, especially for the future standardization work. Okay, but let's start. So this is kind of briefly the roadmap towards 5G. So basically, we have 3 areas that we have to handle in order to get there. So it's the network architecture, it's the air interface, and then it's the spectrum. So this is a kind of coarse classification. So I wonder if this works. No, this laser doesn't seem to be working. That's not good. Well, it doesn't work well. Okay, anyway, so for the network architecture side, already in 4.5G we are going to virtualized core, and actually from there it's not such a big step towards 5G as long as those functionalities are standardized. So then making a virtualized core that handles both LTE and 5G functionalities is thought to be the way to go. Then for the air interface, so as you know, there's this now new air interface being developed. Already in release 15, there's something in that direction. And that will kind of coexist with LTE, which is also evolving as a radio interface, and they will coexist. And then for the spectrum, I think the most interesting really kind of addition from 5G is this kind of millimeter wave spectrum above 6 gigahertz. But this sub 6 gigahertz spectrum is going to be extremely important also for 5G. Okay, so this was maybe a bit boring stuff, but let's now take a look at future of mobile broadband. So if you first look a bit at the right side of this slide. So if you think about virtual reality, and if it's really supposed to be virtual reality, it should be photorealistic virtual reality. So the way how human eye works, there's an area of about 6 degrees of this kind of area of accurate vision in your eye. And in order to do kind of imaging properly for that area, you need more than 1 million pixels. And imagine with virtual reality, if you just turn your kind of vision from one point to the next. So you have about, according to some neuropsychologists, you have something like 13 milliseconds max when the image need to be kind of updated to respond to that new location. So if you move more than 1 million pixels in, let's say, in 5 milliseconds, you actually need something like 16 gigabits per second. So now you may say that, okay, but then we can use compression. But no, video compression is based on the fact that the frames are almost the same. This is a new frame that you have to create. So already from this simple thought experiment, it's very clear that proper virtual reality will require really huge rates, and even lousy virtual reality will require very high rates. So now, okay, if at the same time, if it happens that people really get used to virtual reality, so the current virtual reality devices, they are not that good. It's just in the childhood of its development. So resolution is bad, and the things are clumsy, very expensive, but they are evolving all the time. So it's quite likely that in few years' time, people get so used to kind of consuming their content in virtual reality at home, where they have fiber and very high rates available, so that when they are mobile, so they are not very happy at looking kind of small screen anymore, stamp-size screen on your mobile phone. They might use it, if that's the only thing they have available, they use it, of course, for Snapchat and all these kinds of things that people are using now for social media, but not really for watching content. And basically what I'm saying here, that if we want to have a mobile system of future, it should be capable of doing mobile virtual reality with certain kind of quality. Otherwise, people don't want to pay for the mobile service anymore. Okay, so then we come to the dilemma how to bring such services to mobile users. So there's a lot of kind of talk about massive MIMO, and that is definitely, that's a big step forward that we need to have in 5G in order to bring the capacity. But massive MIMO suffers from some serious problems, and that comes from the fact that it's using the radio channel in a very efficient way. So it means that the radio channel must be known very accurately. So basically this graph here shows that if you use, for example, zero forcing techniques that give the highest kind of capacity in 5G and in massive MIMO systems, so if you start moving the user even at 10 kilometers per hour, so you are not able to track the channel of large number of users who want to get high rates for virtual reality, for example. So the capacity drops, it collapses even. You can do something about this, but you cannot do very much because then you use more and more capacity for channel measurement. So this is a serious problem, because I think we want to make 5G a mobile system. Okay, so what to do? This may be a surprising reason for densification, but according to our studies, this is the only solution to this problem, really. We need to densify. And actually, dense outdoor networks will solve this mobile problem, this mobile capacity problem. Because in a dense network, and I'm not talking now about a headnet with macro and hotspots, I'm talking about this kind of continuous UDN, where you have more or less always line of sight available. So in this kind of network, you can actually maintain very high rates also for mobile users. So for people who are in buses having nothing to do, people kind of traveling in cars which are driving themselves in a city. So those are exactly the people who are the most bored, and they need the entertainment from the internet. Okay, so that's one reason to go to densified network. The second reason is going to millimeter wave access. So I know that many operators say to us vendors that, okay, please make this millimeter wave access so that we only need our current sites. Sorry to say, but this is impossible. Nature is on the way, so it doesn't allow this to happen. And as an example from this is pretty old measurement from Rapaport, pretty pioneering work about this kind of millimeter wave communication in New York. So the path difference, if you have a kind of a macro system or very dense system with line of sight, so the difference in path loss is something on the order of 70 dB. And that's a huge path loss difference. It's huge. So basically, if you don't use that to your benefit, then you have to use, let's say you may have to use 40 dB higher antenna gains and 30 dB higher transmission powers to compensate for this. And actually 40 dB higher antenna gains means that the tracking and discovery is 10,000 times more difficult because the beams are so narrow. So I think nature is telling us clear language that, come on guys, if you want to do millimeter wave access, you have to densify, and you have to densify a lot. You have to go to loss line of sight. Forget about the non-line of sight. It's not going to work. Okay, then you might think that, oh, this is all nice and academic, but then how to do this? So we have done some kind of analysis, and we are not the only one, definitely, which indicates that really the way to do this kind of stuff is use the lampposts. Maybe even use the street lights for radio access in future. So actually you don't have to be Einstein to kind of do the calculation, which actually indicates that this kind of street lamp deployment can be cheaper to do than a dense macro with massive MIMO. So it's not necessarily kind of a killer of the business. There are many nice things about these streetlights. They have power cabling available. The site acquisition is very efficient. So this is actually very important. So you don't need so many lawyers and so many lawyer hours to do this, because you make a single deal, maybe with the city, and then you get access to maybe 100,000 lampposts in one go, instead of negotiating with every house owner separately. Then if you dimension the system right, then you can have this kind of graceful degradation. So you don't need to have site visits. So basically you let the base stations die eventually, and then maybe when 1/3 of them are dead, then you go and maybe replace all of them like light bulbs. So OPEX is in this kind of system can be very low. No visual footprint if they are combined with street lighting. And then there are also other nice possibilities. Of course, then you think that how to do the backhauling. So we have done quite a lot of work to study the backhauling issue, and the cheapest way is to use millimeter wave wireless backhaul. So we believe that it's possible to do that with reasonable cost. Okay, so what else then you can do with this kind of dense network? So I think this is very important for 5G. So if you have a dense network with a lot of bandwidth, it's fairly, I would say, fairly straightforward even to make very accurate positioning system, kind of terrestrial positioning system. It's at least an order of magnitude more accurate than GPS. it consumes, I would say, 2 orders of magnitude less power on the mobile device side. The problem with GPS is that the signals are pretty weak. So that creates a lot of problems and creates a lot of power consumption issues. But here the signals are not weak, and you have plenty of bandwidth available in this kind of system. And this is not only for kind of smartphones. This is also for all the trillions of IoT devices that there will be. So you can measure their position very accurately. I think this is something that we should build in the 5G right from the beginning, because when the 5G infra has been built, it's not that easy to do it afterwards. We should kind of design it into the system from the beginning. Okay, then one more reason to go for densification is the coming death of Moore's law. So I have met many people who say that, oh no, it's not gonna die, it's not gonna die. Well, I think this time it's actually going to die. And this is a pretty nice figure from Arne Mämmälä, but this is based on kind of well-known stuff. I think most people who have really studied this problem, they know about this. And so the problem is not the kind of really that we couldn't scale the computations. It's the power consumption of the computations. So the power consumption of single logic operation. So now with the ever increasing amount of data that goes through the baseband, so we should be able to bring down the amount of joules we use per bit, maybe by a factor of 1,000, in order to compensate for the increasing traffic. But now from Moore's law, we are only getting maybe an improvement anymore by a factor of 10. And then we are at the point of 4 nanometer line width and close to so-called Landauer limit. And then we cannot improve anymore. So what does this to do then with UDN? Okay, so first, if you have a lot of line of sight, and if you use street lights, if you go outside in a city at night and count how many street lights you can see with line of sight, you can see pretty many. So if you don't even need to use every street light, you still have line of sight available, more or less. So line of sight is really nice. And low pathos line of sight, there's no substitute for a line of sight in communication, actually. So in this kind of system, you can have really simple baseband processing. You don't need fancy algorithms that need to pick the signal from really kind of massive mess of kind of multipath. The other thing is that the transmission powers in this kind of system are very low. So it's quite actually it's obvious that you could do a base station unit that is capable of operating maybe with 10 watts in this kind of system. So now if you have 300 of those per square kilometer, so then you consume 3 kilowatts per square kilometer. So then if you have 10 macro base stations with 2,000 watts, that's 20 kilowatts. There's a big difference. Even a simple calculation tells that UDN is very power efficient. Okay, then this is about the new role of future base stations. So they won't anymore just be moving bits. They are the essential infrastructure to build future services. And as an example, I show here a bit what could happen in a mixed reality system in the future. So the base stations, for example, they can be measuring this kind of 3D point cloud, 3D modeling of the environment in a dynamic way all the time. Then you have mobile edge computing that is doing fusion of the data stream with this kind of 3D model of the surroundings. Then you are measuring the kind of the position and orientation of the augmented reality headset with this system. And so it goes. So it means that in future the access network can be a really significant part of creating the service. Not just moving the bits, but it's the essential thing of making future services. So this is a big change in thinking. So it's really a programmable platform of doing all kinds of things, from positioning to mixed reality computation, knowledge of the kind of local discovery, knowledge of the local environment, all kinds of things which are local. Okay, then a bit about microoperators. Yesterday there was interesting talk about microoperators and by Marja, Matti, Mikko, and then really interesting panel discussion where there was a lot of discussion about microoperators. Well, it's actually, we think that it makes a lot of sense to look more in this direction, because it's a way to save costs. So in future, if you think that buildings will have indoor networks, and they will have indoor networks, because that's the only way to build 5G level capabilities to buildings. You cannot anymore do it from outdoor. It has been possible up to now, but now when there's fiber everywhere, more or less, so then you cannot just kind of penetrate through the windows anymore. Even less so with millimeter waves. You start getting reflections, and not only one reflection, you may get many. It's hopeless. Forget about it. So in this kind of system, so if the operators need to build every building, it's very expensive. So I'm sure they are actually quite happy if someone else uses their money to build those networks, and then these operators just buy the access service from these micro operators. So it's actually, I think it will be a necessity in future for successfully working 5G radio networks. So of course then you come to the interesting problem, how to handle the spectrum allocation. So if you have this kind of local micro operators, there's a building, but then you go outside. So maybe a city center is covered by another micro operator. Then you go maybe amusement park, a third one, or you may go to a mall, fourth one. Then you take a road outside the city, fifth one, and so it goes. So there needs to be a way of handling this kind of micro licensing, how to do that. I think that's an interesting problem. Okay, so then what 5G is good for? So I believe that 5G should really be used for applications that require low latency, high reliability, and vehicular mobility. All the rest you can pretty much do with Wi-Fi. The other thing is kind of future IoT, like especially if you want to have truly massive connectivity and then automatic roaming capabilities, because also IoT devices may be moving. For example, if you are tracking devices, tracking shipments, so they are moving all the time. So you need to find ways to make kind of simple solutions for roaming. But as I already said, do not use 5G for trying to penetrate from outdoor to indoor. That's not going to work. That's not a good idea for 5G. Okay, then as an example, in Huawei's Germany, we have been working a lot on this kind of vehicle communication and already using this new radio. So the results, for example, for vehicle-to-vehicle communications, practical results using this new radio interface, so that we can already reach 99.99% reliability, even without retransmission and HARC, with maximum distance of 1 kilometer at speeds up to 170 kilometers per hour. So this is quite promising, and all this with low latency. And then also similar studies about the kind of vehicle to base station communication. So again, at various speeds in this kind of test area, very high reliability, very low latency, and so it's looking promising for NR is looking promising for this kind of usage. And then for Internet of Things, or Industry 4.0, so there are some kind of applications there that require kind of extreme capabilities, like for example this kind of motion control, where the latency may be only 200 to 550 microseconds. At the same time, you should get kind of packet error rates or bit error rates of 10 to minus 8. Very difficult combination to do this actually. Or then another one is, for example, augmented reality or virtual reality, as I discussed. So where at the same time, we need to have extremely high rates, even gigabits per second, and still a low latency, something like 10 milliseconds or less. So this is something that needs much more work also in the standardization still, how to do all this. But really, what is really important to make the IoT work in future, we need to have some kind of capability to have interacting machine-to-machine protocols. Without those, this is going to be hopeless. All the systems are using different protocols. They don't understand each other. So I think this is maybe the biggest challenge. So there is, for example, this Open Platform Communication kind of alliance, OPC, and they have made a standard with this kind of time-sensitive networking. That's one example of solving such problems. Okay, and finally, some recommendations. The first recommendation is that in 5G, we should really focus on mobility, because it's supposed to be a mobile system. It's not easy to build mobility with these requirements that have been set for 5G. So mobility is not a niche. People keep telling me that, 90% of the people are in buildings. Yeah, right, but still you have to solve the problem of mobility, because all these people, they are not all the time in the buildings. And that, I can tell you, those can be done with Wi-Fi. You don't need 5G for buildings, really. This is a bit provocative statement, but it's almost true. Then another thing is that we should pay much more attention to positioning in 5G, because this is an opportunity. We make a new system, we will spend a lot of money spreading that system in deploying it all over the place. So this is an opportunity to, at the same time, build the positioning infra. So we should use this opportunity and not try to do it afterwards, like in LTE. Then you end up with 30-meter accuracy. Here we can do 1 centimeter accuracy if we want. Now, we have to do it now, not later. I'm talking about standardization here. Then I think we should pay more attention to massive IoT for 5G. I think we are now following this narrowband IoT from LTE, but I think we should really, it's a good step forward, but I think in 5G we should start paying more attention on this IoT problem. Then the fact that 5G will be a platform. So APIs, mobile edge computing, all these need more attention that we are paying now. And finally, solutions to support local micro operators. So for example, even seamless mobility between networks. So if you're jumping from one network to another maybe in 30 seconds, so there needs to be good ways of doing that. Okay, I'll stop here. So if you have any questions.
Thank you so much. I hope you have taken note of what 5G will be and what will not be, because it will be interesting to compare when it comes to reality, if you guessed properly or not.
Yeah, right.
Okay, we have time for a couple of questions. I don't see too well from here, but anyone raising the hand? Yes? Okay, can we get one of these mobile microphones there? Yes, it works.
Yeah, I like this. All right, yeah. So very nice talk, Kari. One question regarding the V2V scenario. So that latency that you get, 0.7, that's only for 2 vehicles.
Yeah, it's just for the link between 2 vehicles.
Okay, so right. Now if you put this in real practice, you would have, let's say, hundreds of vehicles, and so how would that latency now go up?
Yeah, that's well. I'm not. I don't know the details how this has been done, but I suspect that there hasn't been too much interference. But remember still that so this is a fairly local thing. So you cannot cram incredibly high number of vehicles in a small space. But it is true that of course if you have a lot of vehicles all doing this at the same time.
And this was what, the traffic safety use case, or was it more input? I mean,
I think this was basically testing the first tests of the NR, so
right.
how well
So
it can handle these things in practice. So
right.
I think those things I think the work will continue from.
Yeah, sure. Okay, thanks.
Okay, any last question? Yes, please. Again, it worked. A marvelous technology.
Thank you. You mentioned the vehicular applications of 5G.
Right.
Do you think the 5G, I mean the ground 5G on the Earth,
Right.
ground 5G is good enough for the future vehicular communication or V2X? Because because we are considering, why don't we combine the space networks, including this aero unmanned flights or any the satellite low, I mean LEO or something like that. So do you think, consider there are any necessity for increasing this kind of space network into this ground 5G?
Okay, very good question. So I think 5G will be deployed in those areas mostly where there's need for it. And if you go outside of those areas, then you have to rely on other technologies. It's like you don't have payment in the forest. So because you don't, it's too expensive. You don't want to have it there. So I think 5G is a bit similar thing. It will mostly first be in cities, then roads, big highways will be covered with it. It's quite expensive actually. But then when you go outside of that area, then I think the role of also satellite systems, especially when it comes to positioning, I think is very important.
Positioning, this will be
no
okay,
question.
good, thank you.
Okay, thank you very much. So thank you for your talk.
Yeah,
and
thank you.
Just as a token of our appreciation.
Thank you.
Thank you.
Thank you.
Okay, so as you have seen here, our next speaker is Mikael. So he's coming from Ericsson, and that's his talk. Yes, so. Okay, you're in charge now.
Great. Thank you, Luis. Good morning, everyone. And first of all, I want to thank Luis and Matti and all the organizers for this great event. I think yesterday's program and also the booths and exhibitions outside, it's making this really a great event. So what I want to do now is to give Ericsson's and my perspectives on where we are on 5G. And I think we all agree that, of course, 5G is about enhanced mobile broadband, but we are also believing that we can solve a number of new use cases. So let's start a little bit to see where we are. This is coming from our mobility report. And I think a good starting point is to notice that already last year we had 400 million of IoT devices that were cellular connected. So this is actually something that will not start from now. It has been happening over the years, and now we see that actually the volumes is picking up. And then we have the prediction back in 2022 that then we will have basically 500 million of 5G subscriptions. So the question is now, what are we doing so that we make this really happening? Because this is, of course, relying on that we, play the game in the right way. And I think, personally, I'm convinced that now we have reached this kind of magic point where we have technology is mature enough. We have 5G, including the evolved LTE. We have IoT that has been cooking for 5 to 10 years, making sensors available and also actually finding the application areas. And we also have the cloud technologies now maturing, making it able to actually scale the size without necessarily having the direct coupling to investment cost. So I think if we take the example a long time ago when we installed the power lines and electricity, I mean, the use case was actually to get electric lighting when it was dark outside, right? And then, of course, it was both technology development and used investment cost getting the power cables into the houses. But once there, then actually innovation spurred, technology developed, and now we use electricity for everything. And this is exactly, I think, the same point in time where we are now when it comes to the connectivity. Technology is mature, the infrastructure is there, but it needs to be further developed, and then this will spur innovation and new use cases. I think all of us, being part of the journey to 5G, we are well aware about the requirements and also the width of the requirements. And also going back to the previous example with the power lines, of course, it would be impossible to draw separate power lines for, different electric applications. And so this is really what we need to do now and succeed with. And that is also to make the 5G platform suitable and capable of as many use cases as possible. So we need basically one system with one architecture, and that needs to cope with all use cases. Then going a little bit into the wireless access, this is how we see it. 5G wireless access, that is of course both LTE and the evolution of LTE, and of course the new radio. But we should remember that during the last years, actually the evolved LTE has spearheaded into trying to support these additional use cases. So here we now have the support for the massive MTC with the narrowband IoT and the eMTC modes. And there we see quite good momentum. And then of course we have NR, then will of course further enhance the mobile broadband experience and capabilities, as well as then shorten the latency and provide additional support for the more critical MTC operations. So a little bit, a few words where we are now on NR and what's going on in 3GPP. Because I think when we went into 3GPP, of course we had all the requirements on 5G, but we also brought with us some design principles that we believe are very important for NR, as well as the evolution of NR. Spectrum flexibility, I think we have been discussing, especially yesterday during the panel. It was obvious that spectrum flexibility is key. Low latency was also mentioned yesterday, obvious. Next one, future-proof design. That, I think, is very important, because one thing that we know, that is a lot of the use cases and so on that we foresee now, they won't happen. But a lot of use cases that we are, of course, looking at now, they will happen. And for sure, that as technology gets there, then also new use cases that we can't foresee today, they will emerge. So we need to, now when we design NR, and this is also something that we learned when we designed LTE, that it's very powerful to keep in mind that we need to keep door open to introduce new modes or new adaptation to make sure that the technology kind of meets also future needs. Ultra lean design, that will of course, I mean, we need to preserve energy and power. I will come back to that later on. And also beam-centric design, or maybe more in general, try to avoid making kind of artificial connection between data and control, or you specify fixed timing relation and things like that. All of that usually complicates things later on especially when we want to, further optimize the technology and introduce additional technology components. And then multi-connectivity and interworking across between spectrum bands. That will be key, because the availability, especially on the highest frequencies or the millimeter wave bands, that will be challenging. So being able to swiftly also rely on lower frequency band, that will be key for the availability and reliability requirements. So let's take a little bit of a look on how it looks. If we start away from a numerology for NR, it is OFDM and base system, and we have the possibility to have different subcarrier spacing. So this means that we actually can adjust and optimize the wireless access depending or for the every specific deployment. Further, the bandwidth per carrier is all the way between 5 and 400 megahertz, depending on the spectrum availability. And if you have even more spectrum, then you basically do carrier aggregation. So I think the intention here was to show that when it comes to the spectrum flexibility, it is basically there for NR. Low latency has been discussed a lot as a requirement. So a few key components to solve this. First of all, there are short scheduling units. So with 60 kilohertz subspacing, you end up with a regular slot length of 125 microseconds. So that means that you basically can imagine that, yes, sub-millisecond round-trip delay over the access is possible. And if that is not enough, we also have the notion of mini-slots, basically going down on single or a couple of OFDM symbol length as the minimum kind of scheduling unit. Fast retransmission. I mean, it's not enough to have the short latency of the air interface. You also need to respond very fast. And that is solved by having front-loaded reference symbols and other information needed to start decoding and demodulation. So that means that implementation-wise, you can basically have like a pipelined solution. And finally, also uplink grant-free transmission will be very important. So if you only have a very tiny little amount of information, you should not have to go through the channel reservation and channel assignments process, but you should just be able to send it up, and if it's successful, you are basically done. That was the latency part. Then we have the ultra-reliable and low latency part. And this is an area that I believe are very important as we are going to connect a lot of value over the networks. Then we also need to make sure that the availability is there. And of course, we all are aware of some techniques. We should, of course, explore all kinds of diversities. We have the coding modulation we can play with. We need enough pilots and so forth, so we make sure that we can estimate the channel. And the multi-connectivity, basically, that we can have multiple transmission or base station points. Enhances the reliability. But one problem here is that all these methods will, of course, doesn't come for free. There will be overhead, additional overhead, or you need additional resources to do this. So there is a risk I mean, basically, if you want, the more reliable you want to do it with a certain latency, it will come with a cost. And some of this cost is probably okay, because it is another service, right? And the reliability is, of course, it's a lot of value in it. But we should, of course, do whatever we can to keep the efficiency as high as possible. And there where the really short latency over the air interface comes in. Because let's say that you have like a 5 millisecond end-to-end delay budget, then we need this fast retransmission so that we can make a couple of retransmissions on the air interface, because that is extremely efficient of actually keeping up the spectral efficiency. So that's a further motivation for the short latency over the air interface. And then we have the ultra-lean design. I guess the most lean way you can do something, that is basically to turn off the transmitter. And that is basically the concept. In today's network, many of the cells are, over time, are periods where they are completely empty. But they still need to transmit sync signals, and they need to transmit system information and so on. So for NR, we don't want to do that. So basically, we avoid as far as possible the always-on transmissions. And of course, that is good from an energy performance perspective, but there are also other benefits. We have the, if you don't transmit, you don't create interference. So you basically increase the achievable data rates in the surrounding cells. And also, this is a very good way to actually do this kind of future-proof design. Because if the devices out there, legacy devices, know that they are nothing there to listen for, then this is, of course, perfect gaps to introduce new technology further on. Okay, so that was a glimpse and some examples of the status of NR and what's going on in 3GPP. And it's a really busy schedule. And as we saw on the timelines yesterday, the target is to have first version stable by end of this year for the non-standalone version of NR, and then mid next year to have also the standalone version. But it's a lot of things to get in place, but I think the progress is quite good, and the industry is committed to keep these timelines. But this is only about specification, and specification is needed for sure. But what is also needed, that is of course to industrialize the technology and get it into products and services at the end. So what we have done the last 5 years, basically, that is all to start the industrialization and early pre-development. Start to work with component manufacturers and so on to make sure that the ecosystem on new frequency bands and new technologies actually get in place. From a conceptual perspective, we also, of course, want to make sure that the technology is will be capable and do what it's supposed to do. So I have, of course, coverage have been one of the key issues. I mean, coverage and deployment possibilities for millimeter wave. So that has been in focus. Also working with the antenna technologies when it comes to beamforming and different MIMO schemes. And then also, of course, the deployment aspects, the outdoor to indoor challenge that Kari raised. Yes, that is a challenge. Sometimes it works, but it's very difficult to, make it work everywhere. And I want to show one example of what we did quite recently. So here, basically, we are on a racetrack, and we did this together with a customer in Korea. And what we wanted to prove is if we can have seamless mobility across different transmission points, and also if we can do beam tracking in a very challenging use case. So basically we have a racetrack. I will start a short video. So what you see is, oh, that was kind of, sorry for that. We need to start it again. Yes, so you see the racetrack. You have 4 small dots. That's basically 4 base stations, and they are performing beam tracking. And then you have a race car actually going out on the straight line of the track and accelerating up to 160 kilometers per hour. And then we are basically monitoring the speed, that's the bottom graph, and you have the throughput on the top graph. So what we see is that, and we have learned that, yes, of course, beam tracking work. It would take some challenge to make it work when the mobility is high. Also, you need to be careful to the propagation, you get a lot of reflection at these frequencies. This is on 28 gigahertz. So sometimes propagation might fool you. So you need to watch out for that. But all in all, we are able to keep gigabits, multi-gigabits per speed, even though in these mobility parts. So this was one example on a proof of concept. So this is of course important now when we come to the industrialization phase. So specification in place, yes, technology slowly maturing and being industrialized in place. But then we also say that we want to address the new use cases and new industries. And that won't happen, by itself. So here we have also during the year started up some industry collaboration, and with the whole purpose to actually approach the other industries that are now thinking of how they should automate things and how they should digitalize and so forth. And of course, we want to tell them about 5G and the prospect, but as much we want to listen to them, because we need to understand what are their pain points, what are their use cases, and what are their visions for the future use cases. And it is, of course, also about finding, what are the different roles here and business models and so on. So I think we have went through a number of different sectors. I think these are not new. I think we all have seen them in 5G related topics, and I think all of them we also quite easily find use cases that make sense or could make sense, because we of course need to verify with actually users of the technology that yes, they believe in the same use cases. So automotive and transport, manufacturing, process industry, agriculture, energy and utilities. And this has resulted then in a number of research projects. So we have a couple of them within the automotive and ITS sector. We have a couple of them on manufacturing, which is one area that also seems to drive very advanced requirements. And we have also been into the mining industry, and we also have some example where we use 5G more for remote control. And some learnings from these activities is that first of all, there is a huge interest for 5G. And many of these industries have been struggling with quite difficult or challenging connectivity situation. Many have used unlicensed and so on, and when they get like an LTE coverage, suddenly, they have stable connectivity. So that has been, so they are very interested. So that's very good. We also have learned that, or seen that, yes, the range in requirements really differs. Some of them are quite, from a connectivity perspective, quite easy to fulfill. So our LTE technology is good enough for many of today's use cases. But there are also others where we actually need the capabilities of NR to fulfill. And not too surprising, we have also discovered the spectrum issue. So connecting back to the vivid panel debate yesterday, there is, of course, we need to get all alternatives up on the table, how to solve the spectrum issues. Micro operators is one good example. Sub-licensing is another. And we also have the kind of shared access scheme with LSA and CBRS that, could actually solve these kind of problems. So there is a lot of interesting dialogue ongoing. But I think that it's very important that we actually engage with the industries And we need to make them aware of our thoughts, and we need to listen to them, and we need to make sure that 5G continue and are ready for their rather next step, not only their today's problem. Yes, so when it comes to research, I mean, we have a lot of splendid, not the least EU projects results that are now going into standardization. We are working on the industrialization and of the technology through test beds and proof of concept. And we have the industrial cooperation. Then we have the standardization that is ongoing. Timeline is, I think, firm. It's really busy, challenging time plan, but we are doing our best to fulfill that. Then when it comes to products, that of course is full speed ahead. And when it comes to the commercial plans, we will see the first trials beginning of next year. And then we are targeting more commercial operating 3GPP based services that should happen in 2019. So, are we then done? Are 5G basically, you know, everything is in place? I want to end with raising some areas that I believe are, you know, very important that we continue to address. First, we have the reliability and availability. I mean, we have an extremely good starting point, I think. Given the telecom and cellular technology, we have very high availability, and the reliability is very good. But all of us that have done some kind of radio network simulation know that, you know, you basically specify the capacity and so on at some outage probability. And if we're now going to hook up mission and business critical operation, that could be self-driving cars or other critical operation, then I think we should do whatever it takes and put a lot of research effort in see how we can, you know, is it possible to take reliability even a step further. Connected to that is security. That is, of course, a continuous fight with attack technologies and mitigation technologies. And the same reasoning with a lot of value going over the networks, this level of threat will increase. And then I think the industrialization enablers for AAS, that will also be a key further down the road here. We talk a lot about multi-antennas, but it's another thing to actually, you know, make it to the same cost as one antenna. So cost level is not allowed to increase, but we want to put hundreds and hundreds more antennas there. So any research on integration technologies, new material for higher efficiency, maybe new architecture, how to actually, you know, that can better avoid that complexity grows with number of antennas and so on, that are very, I think, needed in the second phase where the volumes will come up on 5G. And finally, get the next evolution step of 5G on the horizon. And here we need to work with the industries, look for new use cases, and then, you know, put the technology in perspective of that. And that basically ends my talk.
Thank you, Mikael. I think you stressed that the industry collaboration is really a must for 5G.
Yes.
That's good to hear it because, okay, we'll know about it, but still. So again, questions. Where are the mobile microphones? Yes? Just throw it. Good catch.
Good.
Thank you, Mikael. Very nice talk. Some, not just academics, but some folks have proudly mentioned the term 6G already. If you look far ahead, what is, in your opinion, the major difference between 5G and 6G, what people are now proudly trying to define?
Wow. Oh, thank you. Okay. Yeah, that is of course very good question, and I'm not sure that I'm so much better than you in answering that, right? But as I said, I think we are really in the early phase now when everything going to be connected, and we see a lot of automation and transformation of industry, society, and everything. So given that really early phase, I think we are just at the beginning. Then exactly what that means in technology and connectivity requirements and so on, I think that's very difficult to say. But I mean, getting back to the example with the power lines, I mean, once the light was on in the house and maybe you had a stove on, I think no one could imagine how that you even would drive the cars on electricity, or you would use electricity. You even have solar panels to feed in electricity. So given that point, I'm not worried at all that there will be a lot of things to do, and we will have learned a lot when we will start discuss 6C.
Okay, one more, yes.
Forgive me, I wanted to try and answer the question and not make a new question. For me, the difference between 5G and 6G is 5G is hype, 6G is fantasy.
Okay.
Okay, any other question? No? I see none. Okay, so Mikael, thank you again. And just
Thank you. Great.
Okay, so as you have seen, there's data being generated all over. So we need to know what to do with it. Right, Ian?
That's right.
So again, the control is yours. Please.
Thank you very much, Luis. Thank you very much for having me here today. I used to be a telecoms guy, now I'm a data guy, and this presentation is going to be really quite different to the others that you've seen. Really, it's about why we should care. I'm the first ever Chief Data Scientist for the New South Wales Government, and in fact, the first Chief Data Scientist for any government in Australia. We've been tasked with addressing some wicked policy challenges, problems which are subtle and complex, and ultimately have people's behaviour at their heart. And we use data and data science to try and address those challenges. Data is a way of seeing the world. Science is a way of understanding the world. You bring the two together and you've got some really powerful tools for addressing some really complex problems. And we embrace complexity because the problem is typically not the thing immediately in front of you. The problem is far more complex and far more subtle. And casting an extremely wide net in terms of which data sets you use and the variety of data sets you bring together and the rate at which you bring data sets together gives you a really different and powerful set of perspectives that we've never had before. So this presentation is about why we should care. I'm then going to talk about a little bit about some of the fun stuff that's happening in terms of where we're seeking data sets from. I'm going to indulge a little bit and talk to you about my day job, and then I'm going to leave you with a problem, which I'm hoping you'll help me with. But let's get going. Very first thing is that the world and this clicker are really complex. The world is actually a really complex place. I absolutely love this photograph. This photograph says complexity. This is Brisbane, a city in Australia. And cities are probably the most complex but yet most productive things we've ever created as humankind. And it's really hard not to see this city in a really different context. It's about to get hit by a really substantial storm. But inside all of those offices, there's these points of light, and there are people sitting at their desks, and they're making the world simple. There's an expression in English, keep it simple. Many of us know it. The last word is stupid. Thank you for not saying it. Keep it simple, stupid, because people are bad at dealing with complexity. We really struggle with complexity. And inside every office, there's someone who's making the world simpler so they can plan, so they can model, so they can optimize, so they can make progress. But the realistic situation is that every one of those offices is connected to every other office, physically, by telecoms, by electricity. Every building is connected to every other building. It's a city, roads, sewage, variety of other sort of mechanisms. And as I said, it's really hard not to see that city about to be part of a much bigger ecosystem, which in the short term we call the weather. In the long term we call the climate or the environment. And when we make long-term decisions, when we make decisions which are 10 years or 20 years or 30 years away, then we really have to consider much more of that complexity, so we don't solve what we've all done at some point in our research career, solved a simple problem and missed the bigger point. The other thing about this is it actually says that there are lots of really interesting things about the subtlety and complexity of these problems. Let me go back to this. As I mentioned, data is a way of seeing the world, science is a way of understanding it, and if we're really ambitious about where we take data from, we can bring some really different perspectives on the challenges that we've got. But this city has another perspective to it. We talk about smart cities, smart lighting, smart factories, smart infrastructure, but most cities are actually pretty dumb. Most cities consist of dumb infrastructure. It's not sensorized, it's really hard to optimize. But there's an interesting thing that happens when we bring other data sets into dumb infrastructure. We can actually make it smart. If we can capture information through data about infrastructure, we can start to do planning, modeling, optimization, reconfiguration. We can actually make dumb infrastructure smart by bringing other data sets to bear on that challenge. And if we then take one step further, we can then start to think of infrastructure, smart infrastructure, as actually being a smart service delivery platform. The more of the physical world we can bring into the digital world, the more we can think about that in terms of service delivery or smart service delivery based on digital services, the more we can rethink a smart city or a smart anything as a smart service delivery platform. Now let me talk a little about why we care. There's a few really interesting things that are happening to us as a species. For the first time ever, around about 2009, we became an urban species. For the first time ever, more of us lived in cities than lived anywhere else in any other sort of environment. Currently, there are 7.6 billion people living on the planet. The expectation is that by 2050, so just 33 years from now, by 2050, there will be another 2 billion people living on the planet. No more land, no more water, no more natural resources. It's a closed system, but another 2 billion people. So what we're talking about is sustainable intensification. It also means with this rate of urbanization that most of those 2 billion people will actually move to the cities, and those of us who currently live elsewhere will also start to move to cities. And that has some pretty interesting implications on how we live, how we deliver those services, and how we just get on with each other. There's some other interesting challenges in that most Western economies, there's a challenge with aging. There's something called the silver tsunami coming. Statistically, if you live through today, you get another 4 hours. You may not want it, you may not feel like it, but if you live through today, including this presentation, if you live through today, you get another 4 hours. And that rate of aging is actually increasing. If we come back here in 10 years' time, that 4 hours might actually be 5 hours or even 6 hours. So we are aging as a population in most Western economies. That has implications for a number of different things. One, it changes the needs that people have. As people start to age, more and more people will be living with some sort of cognitive impairment, but will also be living with chronic disease. Things that once used to kill us, we now live with because of healthcare, hospitals, medicines, protocols. It also, though, means we're changing the ratio of those people who are retired versus those people who are working. And at the moment in Australia, there's 7 people working for every 1 person retired. In 20 years, that's expected to change to 5 people for every 1 person retired. And another 20 years after that, it's approximately 3.5 people for every person retired. So we have a productivity challenge. We have a lifestyles challenge. We also have, amongst other things, a clicker challenge. But we have a cost challenge. So some work was done to plot what the cost is associated with just living longer. That's the blue line down the bottom there. And then the cost of living with chronic disease. Those things that once killed us, we now live with. And there was an estimate, the Australian government tried to work out at what point will every dollar that government raises be spent on health. And the estimate was around 2040, 2043. if that trend continues. And that's with the current population. It wasn't an argument about when, it wasn't an argument about if, it was just when. So we've got some productivity challenges, we've got some aging challenges, but we've also got that sustainable intensification challenge. We need to produce more food in the next 50 years than we have in the last 500 globally to support that extra 2 billion people living on the planet. No more land, no more water, no more natural resources. We have what we have. It's a closed system. So ultimately, we're talking about productivity changes and some pretty big changes in how we address the world. But here's a problem. We as people, we as a species are really hard to change. It's really hard to change our behavior. In every modern city in the world, except Oulu, but every other modern city in the world, this happens every morning and every afternoon. And we all know why. Work starts more or less the same time every day, school starts more or less the same time every day, and despite all of the wonderful telecommunications capabilities to date, where we have telepresence and voice and WebEx and goodness knows what else, we don't yet have high quality enough presence to make it actually seem like we really are in the office and get all those side interactions that you have when you're physically there. We are at a 5G conference in northern Finland. We are physically here, not just to share information, but also to see the midnight sun and to enjoy the delicious banquets that are put on. But we still come together. We will never get over the need to come together. People are really hard to change. But when we shift out of the physical world, we live in the physical world, when we shift out of the physical world, there's some interesting things that happen. So I mentioned that if we can bring more of the physical world into the digital world, if we can virtualize more of the world around us, if we can keep that system as closed as possible in terms of bringing everything in and not having to break out, or not having to break out very often, we get some pretty powerful advantages. The first thing is that things really speed up. We collect and process at gigahertz speeds, and yet if it takes you 15 minutes to make a decision, write a letter, send some correspondence, if it only takes you 15 minutes to do that, between those two ends of the spectrum, there's 12 orders of magnitude. Collect, process, compute, gigahertz speed, make a decision, write a letter, read an email. If it's only 15 minutes, that's 12 orders of magnitude. So every time we have to break out of the digital world, we slow down by a million times. And there's a lot of stuff that we do that takes a lot longer than 15 minutes. So we can be talking about really substantial orders of magnitude. So the more we can bring back into that digital world, the more we can keep that fully enclosed, or more of it enclosed, the more often we take advantage of that really powerful speed up. There's two other things that happen. The first is that if we really connect, if you have a reliable, affordable communications, then there's no such thing as the middle of nowhere anymore. Australia has long suffered from what we call the tyranny of distance. Those little points of light are the major cities around Australia. There's a long way between each capital city. Moving physical products around between those capital cities has always been a challenge. Moving them overseas is even a greater challenge. But if your service is digital, it can be generated anywhere, it can be consumed anywhere, and you can create value in completely new sorts of ways. But there's no such thing as the middle of nowhere anymore. The second point is that if you look at your service delivery model and the value that's being created, you can do more than just digitizing what you've always done. That's an old thing in a new way. But if you're really looking at the full complexity of the challenge and thinking about a much more digital world, you can actually create new value in completely new ways. You can do new things in new ways. Now, in order to back up some of the stuff I'm talking about, the day job that I live with is trying to bring data sets in from a variety of different sources. We'll take them in any shape they come. We'll take them real time, we'll take them on magnetic tape. We've been offered punch cards at one point, but we'll take them in any form that they'll come. And what we do is we're looking to, first of all, digitize, learn something about that subtle space, link it, which is where the power comes in and how it reconnects to an event like this, but then do some really powerful stuff, the model, the predict, the personalize, the optimize. And really, it's about evaluating, understanding, predicting, doing the what-if scenario of the world around us. So let me talk about digitization first of all. Everybody, most people will be familiar with LiDAR. It's a really great invention where you can put a spinning laser on the ground and you can create a 3D map. There's some really powerful work that's been done. And that's a really interesting way of capturing the physical world into the digital world. But this is one of my favorite examples of actually making that not a cumbersome, difficult process, but something you could do every day. The guy in the top corner up there is holding something called Zebedee, and I encourage you to have a look at it. CSIRO's Zebedee. CSIRO is Australia's version of VTT, and it's a spinning LiDAR on a spring. And you walk around, and you quite literally, in real time, can create millimeter accurate maps of the world around you. That thing up the top there, of course, is a Boeing 747 as it's being constructed on the factory floor, and the intention was to look at the undercarriage as built versus as planned, start doing defect analysis. That top left, Leaning Tower of Pisa, this was the first time the Leaning Tower of Pisa was ever been mapped from the inside. So we had a volunteer, and I swear it was a volunteer, who travelled all the way from Australia to go to Italy, to go to Leaning Tower of Pisa, run up and down the Leaning Tower and create this map. He waved this thing around inside, he waved it outside, and produced a map of the Leaning Tower of Pisa in 3D with millimetre accuracy in 8 minutes. Now apparently he had to do it in 8 minutes, there was a guard chasing him, but still we've got then the first ever millimetre accurate map of the inside of the Leaning Tower of Pisa. And that bottom corner was, the guys went to a conference, and just to prove they could do this stuff, they walked around during the coffee break and created a 3D model of the conference centre. Fun stuff. But that's an interesting way of capturing data. But the question is, why stop there? This is a real photograph. This is a bee with an RFID on its back, and it's being powered by an energy harvesting device. The business problem we were looking at was what's happening to the global honeybee population. Much of the fruit and vegetables that we eat are pollinated by honeybees. The world populations are declining, and the question is why? And the answer is we don't know. So what the guys did at CSIRO in this case, they put backpacks on 150,000 bees in Australia and in the Amazon jungle, sent them out, and the bees did what they did. They foraged, they went to flowers and so on, and then they came back to the hive, and all the data about what they were doing was then uploaded onto the internet. Each one of these bees is IP addressable. You can update the software on the bee if you want to. And of course, we found out a lot about what bees do during their days. Bees have sick days, by the way. Bees will move between hives on a horizontal basis. They won't move between hives which are vertically separated. Who knew? The data is being analysed at 15 different research centres around the world. It all gets uploaded, and these different research centres get access to all of that honeybee information to try and understand what's going on. But the question for the guys was, why stop there? They took it one step further and then started putting RFIDs on mosquitoes. And I have really no idea how they did that, maybe spraying them around. But they put RFIDs on mosquitoes, taking that extra step. So that's really an Internet of Things. That's an Internet of little things. The data starts to become useful when you connect it together. And this is the reconnection point with this conference. Data becomes useful when you link it together. Data carries information if it captures an event which happened with low probability. But it's when you link it together that it becomes powerful again. And the views that we've heard about over the last couple of days really speak to so many more different sorts of connectivity, qualities of service, data rates, number of devices, battery life, et cetera, from really, really low to really high, really dense to really sparse. And there's some really cool ideas you can have about what you can do with that. Cisco connected some garbage cans together in Barcelona some years ago to help with the garbage collection, not delivery, yes, collection process. And it was essentially to help with the travelling salesman problem. I'm full, I'm not full, the guy next to me is full, but he's not telling you. It helps with the optimization problem. But what's interesting about that is connecting simple devices with a few bits together suddenly allows a new service type. Now this is a really fun thing. This is a fridge. This fridge is connected to the internet, and this fridge was busted sending 750,000 spam emails. Now some people thought this was a new front on a Cold War. Other people realized that what was happening here was a smart device with reliable connection had a brand new service delivery type, a brand new service model. I guarantee you the manufacturers of this fridge did not think they were creating a spam bot. We all know the sort of spam messages. Hello, I'm a Nigerian prince. There's $20 million in the freezer. Put your credit card in. It's a brand new type of service delivery when a smart device is connected to the internet. But then the internet has been around for quite a long time. We used to have the internet of people. From Australia, I'd write to my friend Matti, hey Matti, how's it going in Finland? He'd write back, it's cold, it's dark, stop asking me. Then we had the internet of things. We start to connect devices together. We've all heard about the fridge and the toaster. What would a fridge say to a toaster? But we've heard about the fridge and the toaster. Now we're connecting ourselves. So this is something taken from the IEEE Spectrum magazine from a little while ago, where we can stick on tattoos, which will measure something about our environment, sunlight, UV exposure, skin temperature, level of sweat, and then broadcast it using a little patch antenna back to some other part of the internet. And the interesting consequence of this is that we have made ourselves a device. Now, we might generate this data in order to get some personal information about our health, about performance, about our environment, but we're connecting ourselves. We're not writing emails, we're not interfacing. We are the device that's being connected to the internet. Now, apart from that being really interesting, we've gone full circle where we are the device. We're also starting to talk about sharing some very personal data. Your heart rate, your environment, how much you're sweating is really very personal information about you. And that starts to get us into the interesting challenge that I'm going to leave you with, but let's just take that as a warm-up for the time being. So, digitizing the world around us, we start to see the world in a different way. If we're really ambitious about where we take data from, and our team goes absolutely crazy thinking about the data sets we could bring to bear on a challenge, the value comes when you link it, but then the real value comes when you start to do things with it, the model, the predict, the personalize, or the optimize. So I'm going to talk a little bit about my day job and some of the projects I'm doing in my day job, just to give you a sense of how we're seeing smart cities. The projects we work on range from fire and rescue response times to transport optimization to builder insolvency to domestic violence to identification of children at risk of harm. We have a really broad spectrum. We bring data science to all of those, and the data that we look for is absolutely the widest net we can cast, the better. So a few of the projects I do as a day job. The first one was try to understand the population. We have an area south of Sydney. Any of you who've been to Sydney or landed at the airport, taken the train in, will have passed through this area. It's the most densely populated area in Australia, and it's becoming acceleratingly more dense. And when people were planning for the communities in this space, they made a couple of assumptions. The way you plan communities is you look at what we have called census information. So every 5 years we do a survey. Then you put in place your estimates of births, deaths, inward migration, outward migration, and you project forward and say that's the population. In this case, not only are we still relying on 2011 census information, there was a fundamental assumption made that parents would not have children and live in apartment blocks. This is now the most densely populated area in Australia, and there's no school, because of course parents won't have children in apartment blocks. They also didn't appreciate the rapid intake of people as those apartment blocks were built. So in this case, we looked at using data from a variety of different sources to try and understand the community population, who lives where with whom, at a level of detail which is appropriate for planning schools, hospitals, roads, transport, water, electricity. In some cases, 20 or 30 years out. So we did a range of different things, but the one which is really interesting in this case, we did machine learning against a lot of data sets, but we built a synthetic population, we let them loose and saw what happened. But we used telco data, and we built a 15-minute by 15-minute population model of that area. Who travels in, who travels out, who stays put on a 15-minute by 15-minute basis, aggregated up to what we call SA1, so there's no personal information. But we worked with an Australian telco to build that 15-minute by 15-minute model by gender and by age bracket to try and understand the community composition to help the planning process. We also worked with bank data to try and understand preference, so we could see whether or not people were buying the sorts of things that indicated they had children. Another project we worked on was to try and now predict certain outcomes. In this case, it was predicting pedestrian deaths or predicting aspects of safety. 2011, 2012, 2013, 2014. a decline in pedestrian deaths. 2015, 100% increase in the Sydney area. 2016, another uptick. Many people said it was because of mobile phones. Some people said it was with people using Pokemon Go. No one really knows why. So we've used hundreds of data sets from a variety of different sources to understand the temporal spatial factors of risk, every square metre of Sydney, for every hour of the day, what are the irreducible factors of risk, and then overlay on top of that the journey of a child going to school, someone going to work, someone coming home from work, someone going for a Friday night out, and have built predictive models as well as these temporal spatial models of risk in different parts of Sydney. Telco data, again, is very, very useful in that case. And the last project I'm going to talk about, and I'm taking a little bit of liberty here, is to talk about that Children at Risk project. In New South Wales, there are 22,000 children who've been taken away from their families and put into some sort of protective environment. It costs the state $1 billion a year, and the system is so badly, performs so badly that it was recently declared that it had to be fundamentally reformed. What we try to do here is build the journey of the child and their family through the lens of as many data sets as we can get, and then predict movement through different stages of that child journey. And we talk about first contact with the system. It's called out-of-home care. First contact with the out-of-home care system, or final contact with the out-of-home care system. And we can do it. We've just about to finish the results. We can do that with really high accuracy. 90-something% confidence we can predict where a child will wind up if they've had contact with the out-of-home care system. Adoption, return to family, age out, stable placement. It's extraordinarily powerful because we're using so many data sets and we're using really interesting analytical techniques. But now I'm going to talk about the problem. We can't do those sort of projects. We can't keep doing those sort of projects without talking about privacy. And there are some really interesting challenges in privacy, which as an engineer, as a telecoms guy, I had no idea about until I started doing the work that we're doing. We asked for information about household connections, disconnections to model the population. We just want to find out whether or not people are moving in, people are moving out. We asked a state-owned corporation, can we have that data? And the answer was, no, that's private. So we said, okay, let's aggregate it over 3 months. No. 6 months? No. 12 months? No. 24 months? Maybe. We said, when did we cross the line? When did we move from talking about private data or data which contains personal information to not being concerned about it? And the answer is no one knows. There is no unambiguous test for the presence of personally identifiable information in sets of data sets. When we look across the spectrum of open data to aggregated or obfuscated, highly aggregated, obfuscated, lightly aggregated, obfuscated, to personal with health, there is no unambiguous test for the presence of personally identifiable information in sets of data sets. I was absolutely flabbergasted. So we've started trying to tackle this problem in order to allow smart services. Smart city, smart lamp, smart kettle, smart hot water system, smart factory, smart city, smart government. It all depends on sharing a lot of data, and there are some fundamental questions which we need to answer to see whether or not there is personal information in that sets of data sets. So we've got a group working together in this space. It consists of, believe it or not, lawyers, academics, technical people, regulatory people, information theory people, and I thought the problem originally was an information theoretic problem. I thought that taking sort of the reverse of the information theory mapped to data, if we reverse that, we could simply determine whether or not there was personal information. But it turns out to be a really complex problem. It's an information theory problem, it's a regulatory problem, it's a cultural problem, and there's a few other dimensions thrown in there. And some of the challenges we're looking at are how do we work our way through the regulatory position of the world which was designed from a legal perspective in a very old-fashioned, in a different era where data was typically on paper and you could not mix and mash and process hundreds or thousands or tens of thousands of data sets at gigahertz speeds. The most regulation is written in terms of reasonable or likely re-identification of an individual, Tom Smith. And as a consequence of that, the ability to make that decision is based on human beings. And as I said, even if it only takes you 15 minutes to make that decision, that's 12 orders of magnitude. But those of you who've dealt with privacy or ethics will know it's not 15 minutes, it could be 15 months that you're talking about. So every time we break out and have to get a judgment, we know we're slowing down by at least 12 orders of magnitude. So we're looking at how can you decide? When do you lose the ability to determine whether there's personal information in sets of data sets? If I give you one data set, you might be able to make a decision. If I gave you 1,000 data sets and said I was going to link these together, could you still decide? We're also asking some fun questions like, is identification of an individual cohort of one, so record 001, is it the same as identifying Tom Smith? Is it always the same? Another question we're looking at is what we call the radius of convergence. If I keep adding data sets together, will I get to personal information and therefore trigger privacy legislation? And it's not hard to see how you could keep adding data sets and get there, but if I said that there's a chair over there, I could add 100 years worth of weather data to that chair and not get any closer to personal information. But if I said that chair was in the hall at a conference at this time and there was a panel on, you could see how you'd get there. We're also looking at uniqueness. How unique is too unique? The last question we're looking at is trust. Can we automate trust? Can we build SI units for trust? And this is a concept I floated with Lewis during the reception last night, and I think he thinks I'm crazy. So ladies and gentlemen, that's it. That's it. Complexity is our friend. Data from anywhere is valuable data if you link it together. And my great hope for 5G, and then 6G, and then 7G, and then 8G over there in the corner, my hope for the Gs is that we get more and more connectivity, more and more ways of seeing the world and connecting the world in a more reliable fashion, and that helps us understand the world and ask questions about the world we've never been able to ask before. Thank you very much.
Thank you, Ian. I'd like to say for this talk out of the box, in the sense that it was not addressing the usual or the more common to us telecommunication stuff. So are there any questions? No? Matti?
Something dropped.
Where is it? Matti, we can hear you.
So it's Dropbox. When we talk about 5G, and maybe 6 and 7 as well, a lot of discussion is also touching about changes in network architecture. We're talking about cell edge processing, and let's say the local processing of data becomes more and more important. And distributed processing of big data will be coming there. So can you point us particular challenges from data crunching point of view, what these new architectures, what we might be facing, which we are not, as dumb telecom engineers, looking at all?
Yeah, so the conversation yesterday around latency, I think, is a really important one. Latency is one aspect of this need for a distributed system, but the need to process, calculate locally, I think, is a related aspect. So a lot of the stuff that we're doing at the moment is proof of concept. But as we start to operationalize and as we start to build these things out, it becomes very, very clear that we can't collect everything, process it, and send it back. There are bandwidth bottlenecks. It's also hugely inefficient to send the raw data itself. So the edge networks, Cisco's FOG idea, pushing the compute out to where the data is, and then sending back the stuff that you need most importantly. And there's an interesting trend as well. Once upon a time, we dealt with structured data. We do our calculations on it in only one way, and we use something called extract, transform, load to do that. Now, we want the raw data in whatever form it's in, and we extract, transform, load on site as it's needed, and make sure that we keep the raw data always, irrespective of its condition. And that extract, transform, load process will be different for every different use case that we've got. So edge computing and localized processing and maintenance of that crappy raw data are a couple of trends which will facilitate implementation of these ideas.
Yes, Mikko?
Thank you, Ian, for the thought-provoking presentation. My question is related to availability of data. So there's great opportunities, what can one do with the data, but then how do you see the availability of public data for private companies for building on top of that?
That's a very live topic in Australia at the moment. So there's a couple of trends. One is most governments are trying to push more data out to be open, so just make it freely available. And make it freely available currently in a cleaned up state so you have certain quality. But the point about the structured and unstructured is that we'd also like to give access to raw data. There are some companies who are really starting to do powerful things by linking together credit card, bank, supermarket, airline, insurance company, entertainment data. And there's two companies in Australia that are really pushing people in terms of a new area. These companies are growing at rates you can't imagine. It's like the good old days of GSM in terms of the growth rates of these companies. And they're creating huge insights to questions like who's watching what television, eating what junk food, and therefore is going to be subject to obesity or some sort of different behaviour, or subject to respond to an advertising campaign. Who's buying cigarettes in what household which has children? These are the sort of questions that are being asked. And as I said, banks and airlines and insurance companies and entertainment companies are sharing data to create that value. The next question is, well, why can't they have access to government data? And there's a live conversation at the moment as to whether or not government would sell data, would release, would allow data to be commercially utilised, or whether or not we should always just go for the common denominator of pushing out data to the public as open data. And there's the answer to the question, one way or the other, is worth billions of dollars, even in our little context in Australia.
Okay, we have to finish here. So, Jan, thank you so much.
Thank you, Luis.
Before we leave, I know we are already on the coffee break, but just two housekeeping things. One, remember there's a banquet tonight. And the other thing, remember that you should vote for the best booth until the coffee break in the afternoon. And the prize will be delivered at the banquet together with the Wet Paper Awards. So the takeaway from this session is that, if you give me one more minute, is that we start learning what 5G will be and will not be. Then we went through the need of industrial collaboration, and then we got the idea of what 5G is going to be for getting data and how to produce the data. So there is a quote from Einstein that he said that, I don't know what the Third World War will be, but for sure the fourth will be with stones and sticks. I don't know what 6G will be, but 7G would be about the Internet of Molecules, not bees or mosquitoes. Enjoy the break. Thank you for coming.
Just read your name and then sit down, please. So welcome. I hope you had a nice lunch. My name is Marcus Dillinger. I'm working for Harvey in Munich for 5G vertical research as R&D head. And I'm happy to announce also other panelists, like Andreas Kovczak. He's head of the Cooperative Systems and Communications at Volkswagen Research. We have Uwe Fütschler. He's head of Car2X Nokia Germany. Holger Rosier couldn't make it, he went sick. We have Joachim Sachs, he's principal researcher in Ericsson in Chester, and Andy Williams, executive program manager at 5G. So we will have, let's say, 10 minutes roughly from each panelist to present, and then we will have the discussion involving you later a little bit, but first raising questions. What is the big picture of connected cars? You see here a German slide from Continental. They say we have this year or last year the semi-automatic driving. That means we have already some cars which have a good driver assistance systems and support a driver. We have in 4 years, on 3 years, we have highly automated driving. That means the driver could take back his hand and the car could drive more or less a few minutes maybe by himself. And we have, after 2025, we have the fully automated driving. That means the driver could stay away and the car drives itself maybe a few hours or the whole day. So this is a big picture of what we had more or less last year. And we need to elaborate in the panel whether this vision is fantasy or we will have one way to go further. The big picture, actually, what we made in 5GP, this paper was published 1.5 years ago, was to show the big picture, how complicated this world actually is. So we have basically the cooperative recognition, where the cars exchange some information, And you see here the data rates, the delays, what have been estimated this time. So it starts from a few megabits between cars, and also it has some milliseconds delay from car to car. But the big use case actually steps in when we talk about cooperation, negotiation. So we align the maneuver between different cars. So basically, the first step is the first half of the slides, where you just share information. We also call it sensor sharing. But the next, let's say, step is when the brain is switched on and you have to negotiate what you're doing. So what are your driving intentions and what are your driving plans for the next minutes or even seconds? And of course, it's clear everything needs to be connected to the big brain, the cloud server for the long-term horizon or e-horizon to exchange traffic updates, congestions, and so on, which is ahead of you. And we have also somehow the driver involved. So the driver is still in the loop, let's say, as I mentioned, in the semi-automated, fully automated, but maybe not in the, in the highly automated, but not maybe later in the fully automated driving, where the driver could be removed actually. But we should be aware that we have on the left side, everything needs to be made plausible. So the car engine cannot really just listen to the radio and then make a decision on the actuator. It still needs to be plausibilized, whether this command from other cars makes sense. And this also may take some seconds or 100th of milliseconds. So we have here a quite nice estimate of all these interfaces, but we need to see how we can accomplish that. But it's clear 5G can have a big role on these delays. The outline of this tutorial is that we actually have to elaborate also what is the standardization requirement for release 15, 16, 17, and so on, what we see. Are we happy with LTV or do we need more? What about spectrum? We know we have now the big battle at 5.9 gigahertz, where we have unlicensed bands. We have the battle between 11P, DSRC, and LTV. But it's clear that maybe for the future we need also licensed spectrum, where we get some kind of quality of service for this highly automated driving. I think these things need to be discussed. So we need to identify also in the long term what kind of spectrum do we need, how much spectrum do we need for this purpose. And we need, of course, to understand what is the main challenge in general on technical terms. How do we need to modernize the car platform? We always talk about 5G or 4.5, but we need to be aware that also the car platform will be modernized and will have lower latencies in the future. And the third challenges, I think this is the main focus here of this organization, of this panel. What are the, let's say, challenges in general? We have seen we need an end-to-end view. So we have not only the radio, but also we need to understand how the brain in the car on the cloud will work, which algorithms will be there, do we use fuzzy logic, how do we come to decisions, what happens if the decisions are wrong. I think all these topics are relevant for connected autonomous driving CAD. The spectrum options, we have now the current ITS spectrum, you know, the 5.9. Mainly this is unlicensed spectrum, but what kind of, let's say, additional spectrum requirements do we see maybe in the licensed spectrum? And can we come to a good agreement with the operators, maybe to share their spectrum and to have the quality of service requirements we need? And last but not least, what is most important is the business model. So there are many discussions around how much I'm willing to pay as driver if the car drives myself or drives myself. So I have to see how many euros I pay for this 1 hour. Maybe I pay 10 euros, I pay 15 euros. If the car drives myself, I'll not drive myself. So we have to understand what all these things are interconnected. We have, of course, the business models also for the spectrum discussions. Spectrum costs money, as you know. So we have to see how all these things are in the twisted technology, business models, spectrum discussions. This is quite complicated. So we hope that after the panel discussions, we have some kind of clues and we have some takeaways on that. So I would like to introduce Andreas first, that he starts with the next round of presentations. Just see how it works. Should be yours, yeah.
Thank you very much that I get the chance to present our views here. And I hope I can use not this one. It It's not showing here, Markus. Okay, thanks. So again, Markus introduced the topic quite well, and I would like to present some other requirements that we will need to fulfill the use of 5G in the automotive highly automatic driving use cases. We've come a long way. In the past, we had just small requests from the internet. We had some downloads. Then the upload of sensor data for creating, for example, maps increased a lot. So we are part of all the increasing mobility data. In the future, we will do, as Markus said, sensor sharing between the cars. And this will be also a big part of the mobility data. We've shown that we can do highly automatic driving. We've done the drive at the CES 2015 from San Francisco to Las Vegas, 900-something kilometers, without external communication. And we've also shown that we can do autonomous driving on racetracks, and others have shown it too. But this is a prerequisite to get cars released to the public. So they have to be secure and safe without any connections. But will this be sufficient? Will this be attractive to the customer to take such a car? Yeah? I think we will need communication. Right now, we are designing automatic functions in a way that we will always register a failure and then react to this failure and fall back to a safe state. So it means for the electromechanical steering, for example, that if the electric fails, we still have the mechanical steering. It's working not that nicely, it takes more power, but we still have everything under control. Same applies to brakes. So, and if we are going to highly automatic driving, for the steering, we need two motors, we need also two circuits. So what are we going to do? What are we going to do to get communication in such a way that we can register the failure and that we can then react to this failure of a wireless connection? So we think that we can use 5G communication to extend our sensor range, to verify observations that we see with our sensors and that other cars see with their sensors, so making the probability that this object is really in this place much higher. And we want to also exchange and get highly live updated maps into the car. So what do we need to do to get this ISO 26262 concept into this connectivity? So we need to know about the current status of the network and the connection, but we also need a prediction what will happen in the future. And we think the network has all these information about latency, reliability, and the network load. So our proposal is that we combine the functional safety from the car industry with the quality of service of the telecommunication industry so that we can predict what will be the connectivity for the next moments and adapt the vehicle function. I have here some examples that will illustrate things. If we have, for example, extensive cell load in the next cell we are going to enter, then we'll probably have to expect a lower throughput. So doing at this moment a map update that will be broken up in the next cell would make no sense. Either I can reschedule it or I can stop some other services that are not that safety critical. But we need the information from the network. Handover situations will also increase the latency. If I'm doing teleoperated driving and I'm expecting every 10 milliseconds an input from the network, and I won't get it because I'm going to have a longer handover period, I'll probably can fall back into a so-called coasting mode where I'm completely relying on the vehicle, is completely relying on the sensors, and then after 20 milliseconds it gets the signals from the teleoperator and can continue to drive on. So we don't need to do an emergency brake because we have got no signal. We are aware of the situation. Same to possible interference. So if we are doing high density platooning, for example, we expect to have resource blocks in a licensed band where we have where the operator guarantees that no other one is using this. But there may be an emergency there, and we will probably have to expect interference. And so we can increase the platoon distances. So, and we need redundancy. We have ITS-G5 at 5.9 gigahertz in the license-exempt band, where we have a service where we have no quality of service available, and we have the 5G in the 3.5 gigahertz, for example. It's a nice example. I like this frequency because for the automotive industry, it is a nice compromise between antenna size so that we can still do MIMO, that we can still do arrays, that we can't do at 700 megahertz, for example, where we have the range. We can do decorrelated antennas, and we can use the decorrelated time instances for the Höök process and channel coding. So what I would like to introduce here is that with 5G, we not only get the nice KPIs that are promised by 5G PPP, that we will get the exchange of information, that we get an information flow from the network to the vehicle about the quality of service for the next seconds or minutes. And on the other hand, we will be able to give the network the information about what KPIs we really need, not one fits all. And we can also give the network our position now and for the next 3 to 5 kilometers, which means also to the next minutes. So with this information, the network will also be able to reschedule the resources that it has and make use of it in other places. So that finishes my 10 minutes. Thank you very much. Questions or?
Das ist auf dem Server drauf. Wo ist jetzt der? No?
At the moment it's basically 2 screens, so just escape it. And which is your presentation?
Nokia.
Okay.
Just go to the server. I think that is excellent. This one. Yeah.
So thank you very much. My name is Uwe Pütschler, and I would like to extend and complement Andreas' presentation a little bit. And you will notice there are quite a lot of similarities and a very nice approach of views coming together. So, and that's, I think it's a remarkable achievement that we have already got. Let me start with how we see, we as a telecom equipment vendor, the requirements or the enablers, the basic enablers for highly automated driving, how we see it from the different car manufacturers. So today, the basic enablers, sensors and computing, and that's what Andreas said, the car needs to drive itself. But in order to get to the future, to get to high level and fully automated driving with the right comfort, additional enablers need to come into place, like connectivity, like artificial intelligence, or like HD maps. And obviously, we as an equipment vendor, we would focus on the connectivity. What sort of connectivity can we provide to support highly automated driving? And looking at the applications, we've seen two extremes. Let me say it in that way. So one is infotainment in the cars, very important. Nobody argues about that, but fairly straightforward from a requirements point of view. It is coverage mainly. And in many countries, it's still a little topic. But for the applications which are related to safety and also consequently to highly automated driving, other requirements become more important, like reliability, which Andreas mentioned, or predictability of the network. And last but not least, of course, latencies. And these are things which the current networks can't do, at least the ones which are rolled out today. And that's why I risk to say that in order to do next steps and to move in particular that area forward where predictability, latencies, and reliability become more important, we believe that LTE technology, and in particular with the just released Release 14, we have quite a lot of capabilities and features in our hands which we can make available to the car industry to support communications. And that is like edge computing or the V2V element in Release 14. So these are things which are now being available, and it is about us making them available, test them, and deploy them for the car industry. And I've picked a few use cases which we believe are possible with those extensions, still in LTE, and this way we start going towards 5G. The first one is just local map distribution. Andreas mentioned it also. HD maps are becoming so vitally important for automated driving, but they have a static and a dynamic part, and the dynamic part needs to be always up to date in the car, of course. And with the current technology, we are in a position to provide those maps to the cars. Second example, a very safety-related example. So we could provide information from external sensors, for instance, at intersections or at crossings, into the car by processing those sensor data locally and feed them into the cars. Again, something which is possible with LTE technology today. And last but not least, I would like to come back to a third use case, which Andreas elaborated on quite extensively, predictive connectivity. Why it's important, Andreas talked about. Now, is it possible today? Yes, we are working on this to make that even first steps available in LTE. And that is obviously something which connects data which an operator typically has with data we get from an existing connection. In 4G, it's more about informing the car what it should expect on its path. In 5G, I think we will be able to do the next step, and also based on those data, provide feedback into the networks and to adjust one or the other parameter in the network. That is something to come, and certainly a topic for the 5G discussion. But a basic first step could be even done with LTE. So if I summarize, it is important to make first steps now using existing technology or the technology which has been just released, and make it really onto the road so that the car industry can start really testing it and then pre-deploying it. Because we all know development cycles in the car industry are quite long. Safety is the most important topic in this. And if we wait for all the standards in 5G to come and being implemented, then that's far too long. We should start now. Thank you.
So, good afternoon. My name is Joachim Sachs from Ericsson, and I will provide my vision on 5G for connected and automated driving. And I want to start with what is it in the bigger context? What is the connectivity in the for vehicles, for cars that we will see in the future? And I think also that there are basically two main streams, and one is more services which are for the car, more on commercial, for commercial added value, and infotainment is the prime example here. And this is something that will be expected by any car in the future. I mean, the passengers and the drivers of today have a high expectation here. But there will be new services coming and being provided to vehicles, and this can be, for example, provided by the car manufacturers for maintenance or monitoring of the vehicle status and giving advice on service intervals, for example. It can be something like insurances too, for pay-as-you-drive insurance, and it can be completely new service providers which provide some kind of service. So that already is one type of connectivity that will be used in the cars of the future, and in this case it is mainly provided from services somewhere in the cloud. And when we also have the question on, well, how does it all map to business models? It's an area where normal business models apply. You have a service provider, it's the number of entities being involved is kind of limited per service, and then you have a value chain for that, according to which you can derive a business model. On the other hand, we have the ITS services, which have to do with traffic safety, traffic efficiency, and then it's progressively going more towards autonomous and automated driving and more advanced use cases. And here it's more the V2X optimized communication technologies that are needed, and the distribution of functionality, so that there are some services which run more distributed. Distributed, I mean, the logic is in the vehicles, and it's distributed between or coordinated between vehicles, and other services which also are centralized, that you have a cloud service, for example, making or providing a dynamic map. In this area, we are in a situation that there are multiple stakeholders which have something to say in these use cases. It can be traffic authorities, it can be the car manufacturers, it can be the passengers and drivers. And that means it's a more complicated setup from what are the business cases, how should the relationship between the stakeholders be. Some of the more advanced use cases, and I think some of that we have heard before, it's where you can do the remote driving, you can have platooning with see-through. There is advanced driving assistance where you have also sensor sharing and collective kind of collection of sensor information and making then coordinated maneuvers among vehicles. It can be a protection of vulnerable road users in a traffic situation, assistance at an intersection, and accurate positioning is something which is also going to play a role. When we look in the communication requirements here, there are services, so there's communication between vehicles and the network, vehicle to vehicle, to road infrastructure, or to pedestrians. And there are different technology or communication options. So there's the direct communication, which means it's not using a kind of network infrastructure for the communication. And there we have the technologies like the 802.11p technology, or what LTE V2X has standardized now in release 14. And that is basically using then ITS-specific spectrum like 5.9 gigahertz. And we have more the indirect communication, which goes via a network, and there it's basically based on cellular technologies. From the communication technologies perspective here, we see a little bit the options that are that exist. So we have the ITS G5 or 802.11p based specification, a standard that was developed between 2005 and 2010, and has been now gone through a couple of trials. We have the LTE, which was actually standardized at the same time. It was 2005 to 2008 that LTE was standardized. Since then, there has been a continuous evolution of the standard, and now in release 14, so starting from 2015, dedicated activities towards vehicle-to-X communication were introduced, and the first release of the standard has been finished with the both the direct communication between vehicles on a side link without the infrastructure, as well as via the infrastructure. And already now in release 15, next steps of improvements are being currently worked on. At the same time now, the new radio is coming up. So we had a study item in the last release 14, and are now in progress of the release 15 standardization for this. And there are studies to investigate the new services to be addressed in the V2X area with NR, and it's planned that activities on this in standardization will come in release 16, so that by 2019 or so, some standard functionality should be available. Well, what we see from the performance is that here is a comparison of, for example, for the side link communication on the left-hand side on how these technologies perform. What we can see is that, for example, the LTE side link has better reliability in the communication than, for example, 11p, because it has a much more adaptive physical layer that is more adapting to the variations in the channel. And on the right-hand side, we see the latencies that we find in typical LTE networks. These are measurements that were made in LTE networks a little bit around the world, with the median 10 percentile and 90 percentile. But what is important is that, and that is something I want to highlight, is that we're coming now in an area where two different industries really have to do something, where different industries provide their part in building a complex system. And that, I think it's very important that we get into interaction and collaboration between these industries. And there are several activities ongoing, and I think important to mention here is the 5G Automotive Association as a body where we have the automotive industry as well as the telecommunications industry is together to discuss use cases, time plans of use cases as well, what it means for business models and the role that can be done, the business models and realizations that could be found. Also providing back feedback on, do we have the right targets on what we want to do in the telecommunications standardization to address the use cases for connected vehicles of the future. In addition, there are several research activities in joint collaboration. So in the Horizon 2020 phase 2, I guess it will be presented in the next session, we have the 5G car project here, which was kicked off last week, where we have car manufacturers and the telecommunication industries, and there will be the more advanced use cases will be investigated in this project, and there will be 3 demonstrators being developed for managing a complex intersection coordinated maneuvers at a intersection, sensor sharing, and accurate positioning for protecting of vulnerable roadside users like pedestrians or bicycles. Other activities, there are collaboration projects public funded in Germany. For example, the Convex project, which started early this year, which is about testing the LTE V2X standard. Qualcomm is leading this project. Or there's a 5G Netmobile, a BMBF funded project also on future 5G connected driving. But I also want to mention here on the top right side, the connected mobility arena is an activity in Sweden between Ericsson, Scania, and the Royal Institute of Technology. And what is nice about this, it's a little bit complementary. It's about optimization, the efficiency in public transport, like self-driving buses and remote control of buses. Because, I mean, it's not only the vehicles, I think in particular in cities, getting an automation of the public transport of the future is one big area for connected mobility as well. And another project I want to mention is the Nordic Way. It's a project which is involving the road authorities of the Nordic countries, and also Volvo is involved, and Scania, and here. And that is very much providing safety and non-safety related services, where different service providers are providing services in the cloud, and there's an interchange network for providing or interconnecting services that are provided by multiple stakeholders. So a summary, I think the automotive and ITS services are constantly evolving based on connectivity, and it's important that we also continue to evolve the connectivity capabilities in hand with as the services move on. So this evolution, I think, is a very important part. We cannot now put something in the market which does not enable that in 20 years or 10 years we can do something new. So we must have an evolution kind of thinking in the back of our head when we already start deploying services. We have a number of connectivity options. So we have LTE V2X from 2017. Evolution is ongoing. We have NR V2X from 2019. First specification should be available. But I already want to mention, I think it was also nicely mentioned in the presentation before, that already with vanilla LTE, or what NR will do, we will be able to support many network-based automotive services, because not everything is kind of reliable and needs 1 millisecond latency. But what is really important, and what I want to stress, I guess, it's so important to establish this discussion and collaboration between the automotive industry and the communication industry, and also other involved stakeholders. A couple of projects and the 5GA, and that is a good start for this, because I think it's also important that that in the end, vehicles is something very mobile. So if I think of Europe, if you find from the business case or a business setup a solution which works in Sweden, I mean, it would be good if it's harmonized and there's a solution which works at least over entire Europe. So I think that already makes it important that we get the entire industry also across different states on a board, so to get into this discussion. And that was my part.
Your screen. Thank you very much. Yeah, good afternoon. I will try not to repeat too much. It's a little difficult, to be honest. Maybe give a little bit in perspective of an operator. I'm working for Deutsche Telekom, and we are involved in some activities around automotive, as you can see. But I swear, it's not only a German topic, even though our representation here from the German nation is probably pretty big. Let me give a little bit, I think it's also something some of my colleagues already said. It's, of course, autonomous driving that we are mostly discussing, because probably it's most challenging for us. But we have also other, let's say, car-centric services that can be provided. Because we have to think also in the future, if nobody of you is driving no more, for instance, what you want to do the whole time, right? So you're sitting in the car, maybe you need more entertainment. Are our network ready for that traffic load of entertainment? Is a very valid question. And we do believe there's a lot of different aspects coming into the picture when you think about the car. We already have today narrowband IoT that's supporting some car services as parking or something like that, where you need a very limited database. You can think around the car of many different challenges, and you can also think of the car of a really, really big computer. What do we believe how connectivity could look like? If you look at connectivity today, what you can see is that you basically have a lot of cars already connected over LTE, and you have local sensor technology already in place. In the future, we will see more and more coming up, and also it's also a question of evaluation within the cars, of course, how they will be connected. What we see is, and that's what my colleagues mentioned, that's why I want to make it really short, so you have the connection between the cars, you have the connection, of course, over towards the base stations. You can also see connection car to infrastructure, car to pedestrians, and you will have a backend service where narrowband IoT is probably a good solution for that. Since we discussed this already, jump. I would be able to. Yeah. So what is the operator's perspective? First of all, what I find interesting is why do we have so often these round of discussions around automotive? And I think on every other conference, there is going to be a big automotive panel. And probably the automotive industry is one of the most advanced, because probably they are also challenged by a lot of developments all over the world, right? And what we see is a continuous debate between what is the right technology to provide services for cars. So we have the debate between 11P and LTE or 5G services. This debate is not over yet. We have that quite a while. My colleagues mentioned it as well. What we find interesting from our perspective, from an operator perspective, is that we have the feeling it goes more and more towards a mobile solution, this kind of discussion. So whereas when you look at 3, 4, 5 years in the past, we have 11P that was just standardized and had a big momentum. Right now, from our perspective, the industry is moving towards at least an LTE solution, and we understand that as an opportunity. We also believe that a licensed spectrum is very important to have a certain guarantee of services. Therefore, we think is the right direction. What we were trying to do as DT in order to support a little bit the development, knowing that we are only one little player of many, we try to do trialing, yeah? So in order to develop certain ideas, in order to get momentum also in our politics, in our relationship to the customer. We started basically with a trial on a German highway called A9, it's in the south of Germany, where we trialed mobile edge computing in the first place. And also we trialed LTEV on the same highway, because that's declared in Germany as kind of a test bed for Germany. So on the same highway with LTEV, with various car manufacturers then, just testing basically whether we can hit the promises that were made by the standardization. So whether we were able to keep a connection when two cars are driving 250 kilometers per hour in two directions. So overall, you would have 500 kilometers to fulfill. So this is the kind of trials we did. We also participate in the already mentioned European Automotive Telecommunication Initiative done by Mr. Oettinger, I think last year in Barcelona, and also on the 5GAA. And we do believe that these kind of consortia or alliances, whatever you want to call it, is very important to truly understand the requirements. And if I hear Andreas, is also a question of, do we really need this type of latency, or is it probably more important that everything is more predictive? Yeah, if you have a predictive coverage, you probably don't need 100% coverage. At the moment, we don't have that nowhere, right? So maybe it's enough to have whatever 90-something% and then to predict when the coverage will be over and then do certain services upfront. Everything is possible, but we will only find out if we have certain way of communication and interaction with each other. So this is a little bit my plot. This is what when Andreas mentioned just in a different picture, that we actually at the moment look a lot at LTEV. What can LTEV do, and what do the car manufacturer actually need, and whether I can also have certain, let's say, advantages out of coverage. That would be very important for our services. And we do know that LTEV will be well suited for that one. It will take a while, by the way. I mean, we have the standard now in place. The release 14 gives us LTEV standard, but still, just imagine how long it will take that a certain amount of cars, I'm not talking about every car, will have a respective modem. Yeah, so it will not be right away there, but I think we have done quite some steps to get there, to get it standardized, and now is the time to put it in the cars. So, suited for out of coverage as well. This is also one of the tests we did. So you can use LTEV out of coverage. Yes. So we think we are on the right track here. Still something to do, of course, and yeah, looking forward for the discussion.
So thanks again to all panelists. I think it was a very broad overview we got here, and we have now also the questions up in the room. I would like to ask a few questions and then also invite the audience to raise their questions. So please consider it as a really bidirectional interaction with the panelists and yourself. And I think the big issue is we have, of course, the standard finished. This is nice, okay, LTE release 14. But the big issue is about business modeling and spectrum requirements. And we need to understand how much spectrum do we need. We have now something in the 5.9 around 75 or 30 megahertz, it depends how you count it. And the question is this enough, or do we need also other kinds of spectrum, licensed spectrum, for getting a better quality of service and to really enable this future use cases, day 2, day 3? How would you see also the V2V, let's say, importance from your side to run this under licensed or unlicensed conditions? Any views from your side?
So first of all, in the 5.9 gigahertz frequency range, we are taking on safety relevant use cases, we inform about local hazard warnings, and we will do this on the road from 2019 onwards with 11P. But this is just using one small channel there. We can use also the service channels 2 and 3 for doing, for example, platooning. But we also see that for future use cases, we need a business model. So we need someone who really earns money with it. So with the safety relevant local hazard warning, I don't see that really the customer is willing to pay for it. So, but for highly automatic driving use cases, for high density platooning, for teleoperated driving, I see really a business model behind it. So from this perspective, for those use cases, we need spectrum. And I also claim that if possible, we could use the 5G pilot bands in 3.5 gigahertz, because that's where the telecoms of this world want to do the mobile broadband services. But we also have mobile broadband services with requirements. For example, teleoperated driving is an upstream of video data that with latencies below 50 milliseconds. So we need those bandwidths too. And it's a business case behind it. So it's not just a question if we could get another unlicensed spectrum. It's also about licensed spectrum. Where do we do the services?
So in summary, you say you need licensed spectrum for getting better quality of service and for these advanced use cases. Is this what is the common understanding? So the unlicensed is for the day one, for the safety and let's say non-critical use cases, but for quality of service you need a more managed spectrum. Is this your conclusion?
That's our conclusion. We need the unlicensed spectrum for the safety relevant use cases. And we have to think also about future use cases of cooperative driving. And it's not only highly automatic, it's also assisted driving. And for those use cases, we would also need more spectrum. When we, for example, exchange the trajectories of the moving cars, and we want to do this continuously, we have to think about it. It's probably not to be done on the service channel alone, on the control channel. So we would need to think about ways where we can do this. And this has to be independent of an operator. It has to be worldwide in a frequency. So we need to think far ahead to get those resources.
One last question from my side, but also the V2V is for you important as well, direct communication, or do you rely more on the network? How would you see it for 100% coverage?
As Antje said, we will probably have not 100% coverage. We won't get it. So we have to rely also on, the vehicle to vehicle, and we have to rely on the vehicle to network communication. So there is no black or white. There will always be something in between it. And we have our ideas where the vehicles could in the future extend the coverage of an operator in uncovered areas with our own network, which we can create by relaying of vehicle-to-vehicle communication.
Then I would raise my microphone to Antje for the discussions about, yes, you can also, of course, use this. What about licensed spectrum? The C-band has been mentioned. Is this for you a viable option that you not only use it for MBB, but also for ITS purposes? Is this a way you could think about it? Because it's one of the critical points we know.
So first of all, a decision is not made on that one. In general, we hear very well that people are asking for licensed spectrum, and we believe that is the right way forward. We need to see which band is also suitable for a good coverage. Since we're talking about streets and rural areas, we of course have a different situation than if we might talk about cities or inner city driving only. Therefore, since it's an LTE standard, we actually pretty free to use our available spectrum, whichever operator has. But I think there will be a trade-off in the question of how is my coverage with a certain spectrum, right? So that's important for us.
I think that's a very good idea, taking the 700 megahertz to orchestrate the 3.5 gigahertz in the rural areas, where we'll probably have no hardware covering this area at these frequencies. So nothing against V2V with at 3.5 gigahertz.
I take that.
Okay, any views from Joachim and Uwe on this frequency band discussions?
No, I think we discussed.
You discussed? Okay.
Well, I think one big question is what kind of services is going to be provided in what way, and I think there's a shift in going 10 years back or so. I mean, everything was very much on car-to-car communication, and networks were not so much kind of in the view of that. There was, I mean, the ideas of interconnected roadside units and so, but I think the real focus has been vehicles communicate with vehicles, and I think or I see that there's a shift now also in seeing the capabilities of networks are increasing, which means more services can be provided as a network service, and then basically the network only provides the connectivity, and you're a little bit independent of the spectrum. In the city, you can use the spectrum that is available there, which can be in different bands and higher capacity. If you go to rural areas, you maybe fall back to more the wide area coverage spectrum, and the services can then be hosted basically above the connectivity, and it's interconnected. And I think a question is how much will this balance between what is, I think there will always be a fallback to logic which is entirely in the vehicles and communication between vehicles when there's no coverage, and there's also always going to be a fallback in case even there's no coverage at all, even not on the side link. I mean, the cars are automated and have been driving to Las Vegas or in Las Vegas. So I mean, they can always fall back to their own kind of autonomous behavior. But then, for this to scale up into the large system of many connected vehicles, then I mean, or many vehicles, then the connectivity really becomes important for adding the efficiency into this big distributed system, if we call it like that. So I think depending on how much of this is network provided, you get a little bit rid of the spectrum question. Then you only have to consider the car-to-car, which is at 5.9, is the designated band for that, and the rest can be provided with whatever spectrum is available, and that needs to go over country borders as well, and so on. So I think then I mean, even with every tablet today, or you can go over the border and you switch to another operator and get the same service if you connect to the same service. Then it's more about local hosting of services for ITS.
Okay, one question. We have the 5.9 gigahertz discussion, and we know there's a public band. So how can the operators, let's say, leverage on this public band for the overall business case discussion? Is it that you make a service bundle? That means you have this additional infotainment plus ITS services together. How would you see this? Because usually it's a public band, it's not, let's say, an operator band. How you could monetize this? Do you have any views on that, Antje?
Yeah, it would probably be suitable for the less critical applications, as already mentioned. And at the end, it's yeah, you have to solve certain interference problems and so on. So we shouldn't forget about it. But if the use case doesn't have big requirements on reliability, I think there would be a good option to combine use cases, as I said, for entertainment or whatever in the car, where you can say, okay, that is not as critical, that I need a quality of service in that one, and then you can offer a combination, of course, yeah.
This is service bundle. Okay, I would like to open discussions to the audience. I hope we have now enough, let's say, ideas from our side to you. Are there any questions from your side to the panelists? Yes, please. Benna.
Well, thank you very much. It's a nice device. Just thanks a lot for the quite interesting discussions. I mean, the presentations you made, I mean, the various panelists, they are very much centered on the cellular versions, first LTE version and then the 5G type of versions. But we all know that there is a strong push by the automotive industry today to develop or to deploy the 802.11p standard, the 802.11p version. So my question would be simple. What are the possibilities of the two technologies to coexist? Or said in another way, what will be the prospect of 11p deployment to ossify the possibilities for future evolutions into the cellular world? Because this is, at the level of the Commission, this is a question which is totally open at this moment in time, so we don't have any clear answer to that. So there is a part which is really pushing towards deployment of 11p towards safety type of applications. But it is very unclear at this moment in time how far this deployment is going to still support or enable the kind of hybrid systems we are talking about in our official documents, and how this is going to enable or to not to enable the later deployment of the cellular type of technologies that you are all discussing here. But the compatibility, I think it's in the Ericsson presentation that the notion of roadmap, technology roadmap, was kind of outlined. And this is something I believe we miss very much at this moment in time, is what is the technology roadmap in terms of coexistence of the various technologies? Will they complement on a service level basis, or will they provide the same services but for different categories of performances? I mean, all this would need to be specified at this moment in time.
Who wants to answer?
I think the answer from the automotive industry, at least from Volkswagen, is very clear. We'll provide the 11p service, and it's a service where there is really no business case behind it from a telecom operator point of view. And it's free of charge to our customers and increases the safety. So with an 11p device, I will be able to avoid, for example, a side crash on a lonely crossing in the night where people are normally driving at high speeds. So this is something that happens very seldom, and normally in society it's accepted as a risk by driving. So 11p comes in the same region as the safety belt, as the ABS system, as the ESP. So the customers simply expect safety to be there. So if we are talking, and we are now here for 5G, we are talking about business cases, this is something different. And I doubt that those business cases could live in the same license-exempt band as the safety-related business. So it also, from my point of view, makes absolutely no sense to have on one channel 11p, which talks a different language than LTE-V, on 20 megahertz to the side, left or right, doesn't matter. So the thing here is that we think a hybrid system is, on one hand, unlicensed, in the unlicensed bands, safety-related 11p, and hybrid communication and cellular bands where we have business cases in licensed band. We already have this type of hybrid communication right now in our cars where we have 11p. Most of our cars, as Antje mentioned, have already LTE connection to some backend. So that's our cellular case, and this cellular case will evolve in the future. The same applies to 11p. There will be an 11px development where we will look into more technical details, more features for the future. And we are also developing cooperative systems on 11p that could be used there, and if we have more license-exempt bands, also in other bands. So also sensor sharing, object sharing is in the standardization. And 11p has the main advantages. The chipsets are there. We have extensive field tests and we have proven that this technology is working. So that's how we see this thing.
Just have a question coming from a consumer's perspective. What will drive the adoption? So going into the, say, your customers, car customers, why, for what motivation will the initial customers buy 11P? And how will what is a possible roadmap of the technology adoption from a customer's point of view? So for which motivation will I buy 11P in the initial phase when there's no deployment? Will it be mandatory at the beginning? And how will you adopt other standards into the car?
Our experience with mandatory technology is that if I put mandatory technology into the car, the development is really stopped. So we think that if we put it into the car by ourselves, and it will be a feature of the car that we want to give to the customer, it's giving a new way of safety. So in the beginning, there won't be too many cars. We will have this ramp up of cars. But we are also working on this in 11P with the collaborative perception message. Always difficult for me to pronounce. So we have sensors in the car. Those sensors see other objects and will transmit those other objects. So we'll get from the simulations with 10% of take rate on the cars, we get around about 60% coverage. That is normally something that we achieve after 5 to 6 years. So this will also give some perspective of seeing some features very fast. Does this satisfy?
Maybe if I add, I would say that most of the buyers of cars wouldn't care too much what the technology is behind. I think that's clear. And it is also a matter of fact that some of the car manufacturers have already implemented some, let's say, safety-related features using the standard LTE connectivity they have. It's also there. So that's a second point. A third point is, unfortunately, that's a matter of fact, the views also in the car industry are different. Some manufacturers have one view, others other views. And we are far from being fully aligned, even within the car industry on that topic. The good news is that now we have a few organizations in place, and 5GAA was mentioned already, as one very important new organization where the telecom industry and the car industry come together to address those topics. And I think it is worth mentioning that the objective of that organization is not so much making another standard or so, but to bring it onto the road, to make it happen, to address those issues, business model related, regulatory issues, making recommendations, etc. And we have seen already 5GAA becoming active and making proposals, addressing also the European community. So that has got some momentum already, and it will get more. And the nice thing is, 3 European car manufacturers were co-founders of that organization, and now we have already American OEM included, and others. Chinese are part of it. So it has really gained good momentum.
Okay. Any further questions? Seems okay. Please, sorry, yeah. We'll take this mic.
Well, I have one simple question: is that we all know that the cars are all over the world now. How the manufacturer can put this new technology into the existing cars? So, will people buy some independent devices and put in inside their own old card? Or there are some, I mean, the manufacturer will require the customer to install some equipment or not? So that's my question.
I think he's talking about retrofit, right? So about existing, you want to know whether in existing cars there's a chance to get the technology afterwards in, right? Yes. So I guess it's a retrofit.
I think in the American CAMP program, they've looked into this type of retrofitting older cars. Right now, here in Europe, we are not talking about retrofitting older cars. It has something to do with security and privacy issues, for one of the things.
Maybe an additional comment that there are definitely regional differences between the parts of the world. And just look at Mobileye and the sort of equipment Mobileye has put onto the market, and you will notice that some equipment is available to put into an existing car, which is being sold in some countries, but in others it's not sold. So different ways of addressing a topic.
And I would like to comment a little bit. It goes across some questions earlier. I think it's important in this entire connected vehicles and connected transportation systems to maintain the flexibility for technology to develop, and there are quite different cycles. I don't think that, or I can't remember that when ITSG5 or 11P was standardized that anybody was talking about vehicle to pedestrian kind of communication, but now this is coming as something new now, and so in LTV2X it was addressed because then it was there, but we are not thinking of what comes in 5 years. And if I think only about the cellular communication, we were in an EU funded project, Overdrive it was called, on providing connectivity to the to vehicles 15 years ago, and then it was more about bringing internet services and can we do something more. And I think the feedback from the automotive industry was, at least for safety services, it's not so interesting. I mean, the capabilities 15 years ago in the early UMTS phase was kind of limited. We had other projects then 8 years later, and suddenly you saw first potential. Now we are another level of projects later. I think technology develops, and this can be at very different paces. And if and I think there must be the flexibility to do this. If we take the example of sensor sharing and sensor fusion, for me it is not obvious how this is going to develop. For example, if you take analysis of the cameras, which are increasingly in vehicles, you can share this and then have some sensor fusion, but at the same time, vehicles are built for a 10 to 15 years lifetime, and the analysis of the video and making sensor fusion, and so if you have this in onboard computers, I mean, I don't know anybody here who's working with a 15-year-old laptop. Having this cloudified maybe in the future will be something which brings more innovation, because there you can adopt to different technology cycles as they develop independently. So I think how this shift goes, what is more network-based, what is more distributed, I think there will be, well, maybe we don't even foresee exactly how this develops, and I think we must have in the technology the flexibility to develop. And I, for example, in the discussions that are happening we have now standardized in release 14 LTE-V2X, and in release 15, the discussions, what should be added in the new version of LTE-V2X and what should be added in the NR version, the discussion, well, how does it fit back to kind of the evolution and the backwards compatibility and the coexistence in general, is something which is taken very seriously, because I think we must prepare for an evolution of the technology and can't get stuck in getting something now on the market which blocks kind of the evolution for the next 40 years.
Good point. I think we need to discuss in the US we have, for example, 10 megahertz for ITSG5 anti-collision. In Europe we have 30 megahertz for the same use cases. So why there's a large difference? And we know we have now discussion about radio partitioning in the 5.9. So the proposal is from 5G that we have 10 megahertz for ITSG5, another 10 for LTV.
But now is a big battle that this doesn't really work here. There are two different camps. But just raising the point, while the US is surviving is 10 megahertz for any collision purposes, and in Europe we have 30 megahertz for that. This is not an exaggeration. Can't we have, let's say, this band partitioning in place?
Provocative, Markus. I'm not the expert on the American camp system, but I remember the times when in the US they had 70 megahertz for car-to-car use cases, and they had a radio with one channel where they were switching between all the service channels, and they had the service announcement on the control channels, and then were switching for the other 50 milliseconds to one of the service channels. And those service channels were already dedicated to certain use cases. So actually in the US they had the larger spectrum. We started with 30 megahertz with another option of 20 additional megahertz. So I don't think it's that they in the US they have less spectrum which they can cope with. They can still utilize the other 70 megahertz, but the NPRM is just concerning this control channel.
Sure, but there's a big difference. But let's come back maybe to business cases. We talk about day 2, day 3 business cases. How could be in business case be developed in your view? Is it that you pay per hour when you are driven by the car, or you pay a discount? How would you see a business case for automated driving using radio? Is there any views from your side?
We are not discussing business models here, are we? Not yet. I have ideas, but I think it's not possible to discuss them here.
Confidential. Okay. Good. Any views from the audience? Discussions. Yeah, please.
I have a question for Ms. Williams. So actually, Volkswagen proposed a very good requirement about the predictability. Actually, this is different about the things in a general case for AI, because it's a very strict requirement for network. Because in the old time, the terminals, they do not have a very active interaction with the system. So, but in order to achieve this requirement, it means like the system, the network, need to cooperate with the terminal. So this is very, very different from the 4G operational model. So from operator's point of view, what do you think, how operator could digest this requirement, and what is your opinions on this? Thanks.
So we believe it's a very valid requirement, because it would help us with probably not having 100% coverage over all the country. So the predictability of the network becomes very important, and that would be like a quality of service that we could offer. And it depends on the reliability, of course, of that quality of service to be put in place. We are about, so when you ask me about the technical solution, there's several ideas in place. We started testing in order to provide that, because we do see it as a very, very valid request. I don't know if that.
Okay.
Yeah.
Yeah,
okay, maybe.
So basically, sorry.
Please continue.
So basically, operators are fine for such requirement, because it means like you need a lot of effort to change your system and also go to the standardization. So maybe, I don't know if this is also the purpose from Volkswagen. For example, they say, if I get some information, maybe I want to require something which is not the current setup, and the system could also do some adjustment. So basically, it means the terminal can also influence how your system works.
Yes.
So this is also preferred by the operator, or?
So we do support the general idea. We don't know exactly now when and how we're going to do that, but we believe that we need to provide it. I mean, we haven't discussed anything around a cost and related business case for that, right? But we think, in general, for the 5G network, we will have a lot of this type of requirements, that comes with a reliability and a quality for the service that we need to fulfill.
Okay, thanks.
Maybe one provocative question to Anja. We talk about this license shared access discussions, the C-band. Could you imagine to have some kind of spectrum Airbnb consideration that you are the owner of the spectrum, but you are renting it out to the V2V persons? Because the person next to me is always looking for spectrum. And we have underserved areas, non-coverage areas, and we have learned we need licensed spectrum for V2V. So the question, you are the owner of licensed spectrum. Is it possible that you rent it out against money, spectrum to the OEMs, and they can use it against money? How do you rate this idea?
Not at the moment. I cannot imagine that.
Okay.
I think this was really provocative. And our idea is just the other way around, that when we are entering such an uncovered area, that we would still be in a contract where we are using your spectrum, and we still realize that your planning of the resources is still done by you. But we could, on the other hand, think about providing a service in using our vehicles with the technology to extend your coverage or to increase your throughput, and having small cells there that enable you to increase the data throughput in your macro cell.
Yes, that's understood.
Maybe I would like to come back to the question from the lady. The good news about this predictive approach is that we have tested in some parts of the world similar approach, and there's a cooperation between the operator and some of the video content providers, where information is provided about the status of a connection or elements of network status in order to optimize video delivery. So that is not completely the same, but the principle, the basic idea is very similar. That an application gets specific information about the status of a network in order to optimize the delivery of an application.
But this is maybe quite difficult in reality, because then I would maybe change the operator if the quality is too bad. So that disclosing information about the quality of service could be a mistake. I don't know, what is your view on that way?
I think in the future it will be less and less important to differentiate by coverage. I absolutely agree. That's what we do today, right? So if we all in Germany, it's called Connect Test. So if you are the Connect Test winner and you have the best network, you have much better chances to sell. And I mean, we as operators provoke that development. How much it really brings for the customer is questionable, right? If all networks operators every year are working towards their Connect test and fulfill the Connect test, and that's it. I do believe that in the future we will have more things to deliver, which has a lot to do with a software layer that we have to provide. We have to provide capabilities that we have not in the network today. And we probably have to be very, very flexible in order to serve our, especially industry customers' requirements. So I believe it will shift a little bit away from just being the one that has the most square meters covered in Germany, it will also have its importance. Yeah, we will not stop building, but I think it will shift a little bit away from that question, and it should at the end, because I think it's important to provide other things. And
quality of service not only in the radio but also in transport everywhere must be improved. That you can run all these cams, for instance, every 100 milliseconds over the UU-based interface, not only over V2V. But how to accomplish this with 800 operators in the world, of course, is another challenge. Therefore, maybe the OEM people would like to rely on the V2V direct communication to get something done also in underserved or in bad areas. Any questions from the audience? On the left side, two gentlemen.
Yeah. My question is the following. You know, I mean, looking at a car, there is a radar, which is a millimetric wave. Then I come here and you know, people are talking about millimetric wave. You know, from my point of view, it seems that, you know, millimetric wave is a good opportunity to have a, you know, communication over short range. And then the cars are very short. So if we think about, you know, autonomous vehicle, probably they are running in platoons. So now the question, do you think that, you know, what is the role of millimetric wave in perspective for vehicle communication?
So the question was millimeter wave usage in cars
Right.
for direct but also indirect communication. Was
Right.
your
And
point?
perhaps, you know, I mean, cars can be boosting, you know, application for millimetric wave communication.
Anyone who wants to dare to take the question?
So there is already a designated band at 63 gigahertz for ITS usage. Right now, we don't see the maturity of the technology to be placed into the vehicle at the cost. So we are first concentrating on the 5.9 gigahertz. So the 63 gigahertz will probably come in the future, but honestly, I don't dare to give a date to it. I've started at 94 gigahertz in 1987. So, and it took nearly 20 years to go into vehicular radar in a serious product. So for the communication at millimeter waves, it will take some time, probably more than 5G.
I think also now in this discussion we have to think of the different time horizons, and there are things which are still on the very much research agenda, and you mentioned 63, and I think in 5G millimeter wave is being considered in different areas as well. I think it will never be used for very wide area, but I mean you could imagine that maybe if we think broader, that in local areas, maybe the competition in the future is more which is the safest city. So if a city itself makes sure, I guess it's not like if we look at the accidents and the fatalities in the traffic, it is not like it's uniformly distributed over the country. But if every city would only think of the most 3 dangerous intersections and provide a solution for that, for where pedestrians are maybe recognized, I included in local dynamic maps to the vehicles, and then I think with rather kind of modest coverage deployment, you could probably have the highest kind of impact on achieving something. And but then we come into maybe then city councils should be involved in this discussion when we think of business models also as well, because it's maybe on there the competition. So I think we and that is maybe an area, these intersections where millimeter wave could play a role. I think we should be very open in the evolution of what could be the future. I mean, we will have self-driving buses at some stage in cities and so on. So I think that a lot will happen. So I don't think we should be very open to do research on that.
I also I don't want to say 30 gigahertz is not going to happen. When we think about it in a research term, and not in something that is going into serial production very soon. So we can imagine very fast downloads of huge data sets. For example, when vehicles are passing certain places where we constantly need updates of those things. But actually, I don't see it right now. And also with 5G, I see all the research in the 28 gigahertz. I think there are also frequency bands above mentioned, and I don't see very much activity there. So we would also rely on equipment being there.
There's a Last question from gentleman on the left side, because time is now running almost out.
So during these talks, there are a lot of communication models has been mentioned, like V2V, V2 infrastructure. So I'm wondering which one of these models will be more important, because after all, probably vehicle only has one transmitter or receiver to communicate with one of those infrastructure or other vehicles.
Can you said right. What is more important?
So there are a lot of communication models, right? So from vehicle to vehicle, vehicle to infrastructure, vehicle to pedestrians. So, but at a particular time, so which model we're going to use? So I'm sure this vehicle cannot talk to many partners. Right? So,
when
it's always depending on the situation. So you won't have a constant back-end connection. You won't have a constant connection to pedestrians. Pedestrians, there is a very critical thing with pedestrians. You need to localize those pedestrians very accurate, and you need to predict how they behave. And that's really something, a different research field. So there is no connection where you say it's always vehicle to vehicle and always vehicle to back end. It's all depending on the situation. You don't need vehicle to vehicle when you're alone on the rural road, but you can need vehicle to vehicle when there's a road crossing in the rural area and there's coming another vehicle. So vehicle to vehicle in terms of 11P is constantly working. Yeah, we are constantly emitting our cooperative awareness message, but it's not that it is being used at all the time.
Thank you.
Maybe one additional comment. Cars are connected today, and millions of cars, and the number is growing rapidly without having V2I, V2V, and V2P in place. But the cars need to evolve as well, and additional communications come into play. That's why to say one is more important than the other is probably not what is important.
I think we have to stop. Thanks for your attention, and thank you for the panelists. And I hope it was a good discussion for you. Okay, bye-bye.